So what have you? Okay. Yeah, yeah, that is. In such a way that do you need to stay here just to check? It's fine. It's fine. Or give me one chair. So they all. I hope that I will remember this. I don't know. It's fine. I also in Switzerland. So in the document, they told me, yeah, you. It's not. If I can, why not?
You have to divert yourself.
The last one here. It's like it's not here now. Yeah. I wrote based on the simulator.
Yeah, I kind of thinking like 5. Yeah. Yeah. Oh,
yeah, did we say this sort of sponsored or
We say 10 minutes. Long time. They finally fixed it. It's been every day.
That's your 10 years in the area. Yes.
Everybody, we have a very tight schedule today, so I think that it's time to start. So if you could sit, then there will be the part related to the poster session. Thank you. So, hello everybody. First of all, thank you for being here to this workshop, the role of robotic simulator for unmanned aerial vehicles. The main reason behind this workshop is to transfer knowledge between researchers and engineers that already struggle to find the best robotic simulators for their own application. And this workshop will be related, will concern about unmanned aerial vehicles, especially multi-rotor aircraft. I am Giuseppe Silano, and let me present the team that Zoom, so will help us with the question and answer section. There is me, Giuseppe Silano, then there is Chiara and Wolfgang that are among the audience. And of course, we couldn't do this without our steering committee that we are grateful for them. to them, and they helped us in, let's say, organizing the workshop and moving towards the objective. So let me thank the Professor Antonio Franchi from the University of Twente, Professor Gianluca Antonelli from the University of Cassino and Southern Lazio, then Martin Saska from the Czech Technical University in Prague, Gurab Sutakame from the University of South California, Vincenzo Lipiello from the University of Naples, and then, and least but not last, Stefano Framigioli from the University of Twente. So now let me introduce the workshop and the main objective. So as you probably know, simulators are an invaluable tool for the world robotics community, not only for what concern managerial vehicles. So how an ideal robotic simulator should be fast to gather a large amount of data with limited time and computational burden, should be real time to refine and verify the functional operation of the algorithms, and should be photorealistic to minimize the discrepancy between the sensor observation made in simulation and the real world. As you can imagine, to have all these ideal, let's say, characteristics of a robotic simulator is not so that easy, because poses challenges in terms of are difficult to obtain and generate conflicting. Let's, for example, suppose about a photorealistic environment. These pose challenges in terms of the hardware requirements. Also, if we would like to have a real-time simulator, this means that could be the computational burden could be very high. So, what else also needs to be said, that although all the robotics field are concerned by these issues, this is especially true for managerial vehicles where there are agents with a strong nonlinear dynamics. And what is also very important, an open issue, then potential user struggle to find tools for their own application with could be no standard and prone to human error. This is why we try with this workshop to answer to all these, to cover all these points. There is a landscape of robotic simulator already existing in the literature. Here, for example, there are some of them. The first one that was made by ETH Zurich was the RotorS simulator, a gazebo-based simulator, the one on top. Then the MRS system, it also, it's a gazebo-based simulator. It will be the topic on one of these talks. And then Flightmare, that is a photorealistic environment. It also will be covered by one of these talks. So as we can see, there are two main, let's say, simulator. The first one can be robotics simulator. The other one prioritize the rendering, so the photorealistic environment in order to apply any type of vision algorithms. But on the other hand, it requires a huge effort on the computational side. So even if there are some benefits on some, let's say, robotic simulator, there is also a trade-off as the complexity and the computational burden, as well as the potential higher the costs. And on the right side of the slides, instead, we can see the most common robotics middleware that also needs to be taken into consideration when we design a robotic simulator. One of them is the most common robot operating system. The other one, it's YARP. Even if this is not properly meant for managerial vehicles, when you work on manipulators on drones, so physical interaction with the environment, it's quite useful. Then not so that common, but still it's one of the most used robotics middleware, that is Jaeyoung from last CNRS, and then the recently appeared the robot operating system ROS2. So what are the questions that we want to answer with this workshop? First, which the simulator is best for my application? What are the limits? And how it can be customized for my needs? Some elements, as I said, influence this choice. First of all, the robotics middleware. Of course, if we want to design a robotic simulator for ROS, it's different than design the same simulator for YARP or for GNOME. The other one are the skills of the user and the background. Of course, if the skill is very strong in computer science, for him or for her, it could be easier to write plenty of code, a line of codes. Instead, if the background is from automatic control engineer, it will be completely different. movement, and also the robot dynamics, because it might be easier or harder to simulate the drone. It depends on the level of dynamics that we want to visualize. So the key point there is a clear knowledge and experience. There is the need for transfer knowledge and experience from research group that already addressed in various scenarios these issues, and the need to transfer this knowledge and experience to student and early career researcher. So what we want to, at the end of the workshop at least, we hope that the audience will be able to select a simulator based on the typical use cases, and also where the simulation tools for UAV should be ended in the future, like progresses. Let me also introduce the speakers of today's workshop: Tomáš from the Czech Technical University in Prague, Angela Schoellig from the Technical University of Munich, Jaeyoung Lim from the ETH Zurich, also Pix44 core developer, and last, Davide Scaramuzza from the University of Zurich. This is the schedule of today's workshop, so it's divided into two parts. In the first part, that will be related to the multi-robot simulation for learning and interacting, we will have the talks of Tomáš, Báča, and Angela, and then it will follow the poster session with the refreshment between 3 and 4. It will take 60 minutes. And in the second part, instead of this workshop, it will be related to software in the loop and realistic vision based simulation. We will have two talks, Lim and Davide. And then it will follow the core part of the workshop, a breakout session where small group of people, 4 or 5, will discuss the topics that I'm going to present in these slides, and also topics that they would like to address starting from the talks. Then there will be a presentation session where the conversation about this topic will be presented one by one of them, of these small groups. And we start the panel discussion, and then we will close the workshop with the final remarks of wrapping up what we discussed. Important links and info that for this workshop, for sure you can find today's program to the website that is listed in these slides, and also scanning the QR code. Also, let me remind you the open discussion and poster paper presentation. As you can see on the right side of this room, there are the posters. And then for any questions, you can use the Zoom chat. We will take the questions for the speakers immediately after their talk. Here, the suggested topics for the breakout session. So create a flow charts for selecting the right simulator. So how should the new user pick up their simulator? Then which is the best simulator for the beginners, which is the best for customizability, for sim to real transfer? What are the main features that are still missing in the available simulation tools? What are challenges in UAV simulation for application-specific scenarios? Do academic and industrial needs solution match? And should be there the one simulator or maybe different one? So advantages, disadvantages of keeping the heterogeneous simulation landscape. That's all from my introduction slides. I would like also to thank all the projects that were behind this workshop, like Aerial Comfort Drones, FlyFleet, Drone Code Foundation, and that's all from my introduction presentation. So I would like to invite the first speaker of this workshop, and Tomáš, if you can start sharing your screen or stop sharing. Try to share. Maybe if you share, we'll stop sharing. Yeah, because no, wait. Yeah, see? Awesome. Okay, try to share your slides. It works. Okay.
Thank you, Giuseppe, for the great introduction. I think you really hit all the marks of what the current problems and challenges are with our simulations, which is, of course, the necessary engineering part of doing research with drones. My name is Tomáš Báča. I am a researcher, postdoc researcher at the Czech Technical University in Prague. And hopefully I'll shine some light on how we approach simulation within our group. What challenges do we face or are facing currently as a quite large and growing group? And what are my suggestions and maybe some tricks that we currently use to face those challenges? And hopefully in the end, some of you might take some benefit out of this talk. But anyway, if I speak about stuff you already do or already know, that's great for you. And in the end, I hope it's not going to be a boring talk. Just a quick introduction. We are based in Prague, a very nice city in Central Europe, in the house at Charles Square with very limited room for real-world flight. That is why we heavily use simulations, because we actually fly just a few times in a year, and we really need to batch process the flying in the real world. So simulations are super important to us. We are a group of currently 40 people and more than 40 drones. So imagine how such a large group can achieve results without simulations. That's actually not possible. We really need to use simulations from start to finish to prepare for our real-world verification. And a real-world verification is what we really try to achieve with all our research and papers. Because in my opinion, a drone research which does not use real drones is hardly transferable. Of course, there are exceptions, but we really try to base our research on real-world use, and simulations help us to maintain the fleet of drones actually flyable. Before I get into the real stuff, just a quick reminder, we actually organize summer school on multi-robot systems where students and anybody can experiment with our simulator and our drones. I'll get to this in the end, but if I forget, please check the website. I have flyers which I can give to you, and we can meet in Prague in July. So just a quick context, our group conducts research in multi-robot systems. We do everything for swarming, decentralized formation control, through inspection. We also took part in numerous robotic challenges, namely the MDZRC 2017, 2020, which we won on several occasions. And of course, the DARPA Subterranean, which was very recently a huge success for us, because we won the simulator challenge in DARPA with our best drones in the DARPA simulator. So this is our background. Mostly we are interested in multi-robot simulations, but we are of course doing control engineering, 3D mapping, planning. So as Giuseppe said, our use case for simulators is overall, we need everything from the simulator, from dynamics to precise sensor emulation up to multi-robot systems and communications. Our fleet of drones is quite heterogeneous, I would say, from very small drones typically used for VIO research up to super large drones, for example, for other drone elimination and firefighting. The middle-sized drones are used for the typical swarming. So when simulating, we really need to be able to simulate very heterogeneous sensor packages, from LiDARs to cameras, RGB cameras, thermal cameras, depth cameras, up to, for example, radiation sensors. That's our specialty. So this is what we work with. And now I'll present how we tackle the simulations themselves or itself. So technically, the question is what's in our toolbox? And this is sort of a broad question to all of you, and I see some of the answers around. And as a freshman researcher, I would imagine anybody starts with the tools which are provided by community. And as we evolve and as we grow, we start to adapt those tools, create our own tools, and hopefully some of you are also providing tools for the community. And I hope our group is slowly getting to the point where some of you might even be using our system for your own research, which would very please me. To help with all of this, I hope everybody uses automation to help you with actually deploying simulations in the real world. Without automation, everything will be quite slow for you. So our main backbone for simulations is Gazebo, actually Gazebo/ROS, which in my eyes is the Leatherman or the Swiss Army knife of simulators. It can do a little bit of everything for everybody, and it's quite modular. And that's what we have started with a few years ago, thanks to University of Pennsylvania. And we are still using it till today because the group has quite a large inertia, and we yet still haven't moved to anything else. So I'll talk briefly about how we use it. We might be using it in a slightly different way than all you do. And then I'll move to the other aspects of our simulating world. So we use the typical PX4 SITL scheme because PX4/PixHawk is our main flight controller to go, which we use on all of our drones. So we started with the typical scheme where you have the PX4 as the core of your simulator pipeline. And I expect that most of you know that it works by actually first starting some launch file at PX4's repository, which will induce a drone SDF to be spawned in the world and a Mavros node to be launched in your ROS node. I'm talking in ROS1 right now. This scheme is, of course, usable for most of you who do a little bit of single drone flying there or maybe 2 drones there. But it has its own limitations because if you want to customize the simulation, you need to edit several files, mainly the launch file, which defines what drones you need, how they are built, what ports are used to communicate with the components. You also need to have the drone predefined, meaning like what sensors are attached and where. In some of those examples, we can see, for example, Iris drone with an OptFlow sensor. And you also, you need to change anything or everything from this list to customize the simulation for you. And for us, this was sustainable when we had 1, 2, maybe 3 drones in the whole lab. But now with 40 drones, each with a really different configuration, this is not sustainable anymore. So we created our own mechanism of introducing new drones into the simulator. We call it a drone spawner, which sits right here on the right-hand side in our ROS pipeline. It's a node which accepts requests through ROS. So anybody can call a request, please give me a drone. And the drone spawner, based on the request, creates an instance of PX4, SITL, inserts an appropriate SDF model into the simulator and runs a Mavros node. You might say, yeah, this is the same thing that's used by us as well. So what's the difference? Besides being able to run arbitrary amount of drones asynchronously on demand, the main difference is that the way how we compose the drones SDF is dynamic. So we first have a list of possible attachments. So let's say payloads. These might be sensors. These might be physical attachments, like a pendulum if you do control research. These might be whatever you physically mount to a drone, and it might be a pluginized attachment. So there is a list of attachments. They are general. There is no fixed way how to mount them to a drone. So in our group, there is one person who takes responsibility on maintaining the list of attachments, and I might name several of them. There might be LiDARs, RGB cameras, rangefinders, point rangefinders, depth cameras, and so on. These attachments might be parameterized, so camera might have resolution as one of its parameters, so it's really meant to be general. Then there is another list of possible attachment placements on each of the drone's frame. This comes from the physical constraints. So when we have a new drone built, our hardware guys are actually creating 3D holders and mounting points on the drones. They are actually then creating 3D models of these and putting them into the simulator. And then they are defining the relative coordinates of where the sensors are gonna actually be connected on the drone. So somebody has to maintain this, but it can be another person who takes care of the hardware and knows where the sensor is actually placed on the real hardware. So our students don't need to walk around the lab and measure the relative distances from a camera to the drone center of mass every time, because the hardware guys know. And then the mechanism accepts queries from the user, and the user might say, okay, I want to attach an oyster sensor to this particular drone frame, and the system knows where the oyster is supposed to be because it's defined in the drone's attachment file, and it will just connect those two together. And you can specify arbitrary combination of sensors per drone. So this gives us end-to-end relationship between sensors and drones, and anybody out of our 40 people can simulate any drone without actually going into the files, defining how the drone looks like, and playing with like the relative transformations. So this has some potential advantages. We can scale the research, we can scale the group, and if anybody has a problem, he will just tell me, hey, I have a problem, and I use the F450 drone with the oyster and real sense, and I can just plug in the one query into my simulator, and I can recreate whatever environment or scenario he's using. Of course, we can define sensor groups. So whenever we are working on a particular project, and there is a drone built for that project, we know that a sensor group is created, which contains whatever the particular drone uses. So we don't have to remember, we need to have IMU plus LiDAR, for example. So then there is another issue which we solved quite elegantly, and that is how we know where the sensors are actually mounted after the drone is injected into the simulator. That is done by retransmitting the gazebo's transformations into ROS. So anytime we add a sensor, a world plugin in Gazebo listens for the sensor placement on the drone and creates static TF, which we can use in ROS to transform data from the sensor frame to the drone frame. This is very useful because, again, our students or the normal users of the system don't need to know where the sensor actually is. That's not relevant for them. The sensor will appear, data will appear, and they can just use them. So I'll give you a short example. Everybody knows this. That's the gazebo with the default ground plane. When we want to start simulating, you first have to pick which drone you want. So here are a few drones as an example. Those are our typical platforms which we use in the group. You might know some of those. And for each of those drones, we have parameter for the drone spawner. So I'll start with the F450 drone. That's the DJI's frame. And I'll show you a little bit of a live demo, which is typically forbidden in robotics, but hopefully it won't show the dark side of live demos. So I should have a gazebo, fresh gazebo without any drones starting right now. And if I don't know what to do, of course, demo doesn't work well. I started the wrong demo. Yeah, never do a robotic demo. It's not worth it. And this is not even a robotic demo. This is just simulator. So gazebo starting right now. So if I'm just a user of the system and I don't know anything about it, I can just ask for help, and it will tell me what arguments the drone spawner can accept with all the sensors and all the parameters. So I can just decide, okay, let's spawn a drone with ID number 1 and the frame type F450. And if I hit this, launch sequence initiated, I should have a drone appear in the simulator. Now I can asynchronously continue and I can say, okay, give me a drone number 2, frame F450, and let's add RP LiDAR sensor. That's a 2D LiDAR, quite simplistic, but works well for some application. So I have a drone here. Yeah, and I could go on. I could even try more complicated scenario. For example, I could spawn drone with ID number 4 with a different frame type, and I could enable oyster sensor, and I could give it even a parameter which says, okay, give me OS0-64, which is a particular version of the sensor, and use GPU to render the rays. So it accepts arguments and parameters, and it's of course very modifiable. So we have another drone with ID number 4. If I zoom in, you'll see that the oyster was attached to the drone. Of course, right now the ROS is running, so I could start showing you the data, but that's not relevant, I guess. And since I said that we are doing multi-robot systems, this is very handy when spawning multiple drones for verification and simulations. So let's say I want to do 10 drone experiment where each of the drone, where every drone is the same, which is the typical homogeneous swarm example. So I would call a command which would give me 10 drones with IDs from 1 to 10 with a particular frame and a particular sensor. And if I hit it, I should start getting drones being spawned in the simulator. A little trick, which I recommend to do every time: spawn the drones at random locations with random heading, because this prevents users to like over optimize their algorithms. Yeah, to be truthful, it happens often that students somehow expect that the drone starts at 0, 0, pointing at 0, which is of course nonsense in reality. So we have 10 drones, and all I need to do is just hit one command, inserting one query stating I want 10 drones. So this was a huge quality of life improvement for us, which gave us the ability to easily start simulations for anybody with any configuration. And we don't need to see those files which define the sensors and the drones at all. We don't need to go deep. That's a great thing. If you want to replicate it, definitely check our repositories, GitHub ctu-mrs/simulation. That's the meta package for our simulation system. We have also everything wrapped in Singularity if you want just to try it, but not to install it, also very handy. So that was Gazebo. And as Giuseppe asked, is one simulator enough, or is there one simulator which is perfect? I'll try to answer a question with my own words. We often do multi-robot experiments. This is 15 drones flying in a swarm, and simulating swarms is quite painful. And doing that in the Gazebo SITL for us with our complete control system is quite undoable, because Gazebo is easily bottlenecked, and simulating onboard sensors on top of this really kills the computer. So we are searching for perfect swarm simulator. Somebody else might need high quality visuals for doing some reinforcement learning or like visual based control. I bet Davide will talk about this quite fondly. So there are simulators which specialize on this. Somebody might look for example, Coppelia robotics simulator, which is, in my eyes, quite simple simulator, but that's what I would use if I would teach a high school class, for example, because it's very accessible without complicated dependencies. So there are definitely special use cases for simulators. And in my eyes, there is no perfect simulator. Yeah, that's my answer to the question. Some of those simulators appear to be like Leatherman, can do sort of everything, but it's not perfect. And definitely I would not use it the whole day. Some of those simulators are more like toy skits, but they maybe can get some job done. And some of those are very specialized, can be used the whole day, but you cannot hammer with a screwdriver, definitely. So in my opinion, we should use the right simulator for the job. And we are starting to see this in our group quite well, because some of the people like start to reach for those visual fidelity simulators. Some of our people reach for simulators which can support hundreds of drones. And how to deal with this? That's our current issue. How to allow our system, our control stack, to interact with the variety of simulators which is there. As I said, up until now, we were using PixHawk and PX4 as our main drivers. So our system, that's this thing on the right, our control stack, which includes feedback control, state estimation, trajectory generation, everything was sort of dependent on this hierarchy. It was quite okay for the past 6 years, because it was okay, but now we start to see that that it's not enough, that we need to cut this dependency. Because sometimes we don't even want SITL with PX4 attending our simulations. Just imagine simulating swarm with 400 drones, where the control input to the drone is desired velocity. PX4 is not necessary there when the input is desired velocity. So currently we are working on cutting this tie between our system, the MARA system, and PX4, and somehow allowing it to interact with anything that might be on the left-hand side. So what might be on the left-hand side? Up until now, for us, that was desired attitude rate plus throttle input going into some low-level flight controller. For others, it might be desired velocity plus heading. For others, it might be individual actuators if you do racing and fast agile flight. On the other hand, what the underlying platform might provide may differ. Some might provide low-level IMU-based data. Some might just provide velocity of the drone and orientation. So imagine working with arbitrary system on the other side might be quite difficult to do, because not always you are going to get everything you expect to get in your system. So what are the solutions? The basic solution is just make your system work with various platforms. Program it, configure it, adopt it. This is typically done in the first place when you need to work with yet another platform. You program some other functions which will replace the first functions, and you create a config file and you switch from PX4 to whatever else is there. This is fine, but it does not scale well. If you go over few platforms, then you find your system to be really like, not that well written, because there is a lot of ifs. And that's sort of like an artificial intelligence. That's what we have done so far, and it's not good. I don't recommend it. The other option is to create abstractions. Abstractions are important because they allow us to focus on one particular thing. And building abstractions into our system is what we are doing right now. It's still unpublished, so I'm talking about stuff we are actually doing right now. And it allows us to really interface with anything on the other side. It scales well, it removes dependencies. So currently our control core system is really independent on Mavros and Mavling and PX4, and it provides isolation, so we can sort of shield ourselves from the problems of particular hardware. It has its own issues, of course. Abstractions introduce implementation overhead. There is a lot of functions just because of you need to sort of hand data from the left-hand side to right-hand side, and it introduces a computational overhead. How we do it? We have a special sort of a plugin manager as a part of our system, and for each underlying subsystem, it might be PX4, it might be Coppelia-Sim, it might be very simplistic swarm simulator. We need to create a plugin which is gonna plug in literally into our system, and it's gonna maintain the communication with whatever flight controller is on the other side. And therefore, the dependencies, being literal dependencies in build time or runtime, are maintained by the plugin itself. When the plugin is plugged into the system, it tells our control system what are the plugin's capabilities, what it offers, what data it can provide, being a position, orientation, IMU, and it tells the system what it requires, what are the allowed control inputs from our system to the low-level hardware. And after this communication happens, our system can start interacting through the plugin manager with the hardware, outputting control outputs and receiving data. It's very simple to say and to show. I would say it's very hard to do, I can state from experience, because the system needs to configure itself then for the particular combination of control outputs and provided data. Of course, this is not always possible. Some provided data might not allow you to control the desired control output. For example, if you want to control the drone on the actuator level, you really need IMU. Without IMU, you cannot do that. But we have somehow managed to make sure the system configures correctly for arbitrary control output. And what I'm talking about is these are the expected provided data by, let's say, a general flight controller. And on the right-hand side, you see the accepted control inputs from the flight controller point of view. So we expect that the general flight controller can accept anything from desired position, velocity, acceleration, attitude, control group, and even individual actuators. So our control pipeline needs to reconfigure itself to manage to output one of these. And thanks to this, we are currently with our MRSAV system able to fly with different simulators without actually needing to configure anything in the system itself. We can just run our system using a single launch file, and we don't need to explicitly tell it, okay, your control output is gonna be this, but we need to run the correct plugin for the hardware. And in this case, I mean for the simulator. So each simulator / each flight controller needs to have its own plugin, and that could be written by you, by any user of the system, and the system can just control the drone quite easily. So the first thing I have tested after Gazebo was Coppelia, with the hope of using it for our swarm simulations, but I found that it's actually quite slow for multi-robot systems, so not great for us. And then I decided to build our own simulator, which I recommend to do. It's quite good learning experience. And I've built just a dynamic simulator, very similar to Rotor S, written in C++ in this case, full dynamics from rotors up to the position. The simulator itself embeds flight controllers, which allows it to accept any of those set inputs. So if you are a swarming guy, you could use desired velocity as your input. If you really aim for control engineering, you can use individual actuators. Our custom simulator is built into the MRS system, at least into the version which is going to be released, or let's say merged soon. It's still sort of in process of testing. And this simulator allows me to really test our system against arbitrary underlying flight controller, because I can emulate anything using our simulator. So I don't have to run some stuff like Gazebo, which is quite demanding if you really need to test every combination of every input. Definitely check this simulator, because we have built it as a header-only C++ library, so you can inject it into your own code, and you can use it, for example, for reinforcement learning, where you control the simulator loop within your code. I'll show you a quick live demo if I have time for it. Do I? I hope. So having your own simulator has huge benefits. You can control the performance quite well. So what you'll see here is 400 drones simulated with full dynamics, doing some typical Boyd swarming. And this really helps our swarming guys to test their approaches in large scale, which with Gazebo, that was really not possible at this scale in real time. So yeah, definitely recommend to build your own tools, learn from it, and then hopefully give back to the community such that we can always learn from it as well. So this is our current state of our own simulators. And just a little teaser, we are also working on Unreal Engine 5 renderer, very similar to University of Zurich's Flightmare, which is gonna work in tandem with our dynamic simulator, which you just saw doing the swarm. So this is work in progress, hopefully is coming soon during next IROS. Everything I said either is or is going to be soon at our GitHub at C2 MRS. Of course, the MRS system is there, but the abstraction level layer is yet not merged, but we are testing it hard so that we don't destroy anybody else's drone while, yeah, you can deploy it later. Again, I have to say that we are inviting you to our summer school next month. I'll meet you during the coffee break and give you the flyers. Definitely recommend this to your students. Thank you for listening and keep simulating. Do we have time for questions?
Not the time that we planned, but yes, maybe if there is a quick question, we can, yeah, we can. Yes, please. I didn't fully understand in your last work how the different simulators are selected. This is still something that now you presented one that you now implemented yourself, but the motivation was that there could be multiple different simulators.
Yes.
Can you say something about that?
So the selection of the simulator is everybody's choice based on the needs and particular setup. How good fidelity of sensors do you need? How many drones? How realistic dynamics do you need? What level of control input do you need? And so far, I have an opinion that everybody has to select this on their own, and we don't have a perfect simulator for everybody. So in our group, we are currently pushing all those changes to actually support everybody doing their own decision and choice, such that they can actually use any simulator or any underlying hardware while still using our control software, which does all the hard work of mapping, path planning, trajectory generation, control, and stuff like that.
Okay, thank you. Maybe time for another question. Yes, please.
Thank you very much. I see that much of the limitations that has appeared were due to the requirement of real-time simulation. But usually for verification, we don't require that. So we can go faster in step time if we can afford to generate more data, or we can go just slower and have some verification on the functionality on the overall mission. So why is that a strict requirement and it diverted your design choice?
Great question. Of course, I said real time. What I meant is real time or faster, which allows us to actually experiment faster and get more data. The problem with not real time is that it takes time. When we, for example, did the DARPA Subterranean Simulation Challenge, it really took 2 hours to finish one 10-minute flight with their simulation setup. And it was really painful to observe it and do any changes. And it took us months to do work which normally would take weeks, just because the feedback loop of learning and finding mistakes was so slow. So we are always aiming for at least real time, because that gives us the ability to actually find the issues fast. Yeah.
Thank you.
Okay, let's thank our speaker again.
Okay, our next speaker is Professor Angela Schoellig. She's now with TU Munich, and she was for many years at the University of Toronto and has been working on UAVs and machine learning. And today she will present her recent work on using simulation tools for UAVs.
Okay, great. Okay, great. Thank you. Welcome, everybody. So, yeah, my name is Angela Schoellig. I'm now at the Technical University of Munich and still have a team also at the University of Toronto. So today I want to talk about 2 software tools that we have been developing recently, Safe Control Gym and gym-pybullet-drones, both actually with a motivation to interface realistic quadrotor dynamics with machine learning toolboxes and in particular reinforcement learning. So the 2 gym-compatible simulation environments that I'll discuss is gym-pybullet-drones. It's a simple OpenAI gym environment with full quadrotor dynamics. And the motivation was to do multi-agent reinforcement learning. But it generally found interest in the community, I think, beyond the multi-agent reinforcement learning, because it's a pretty simple but realistic simulation environment. And there were also other groups, not our group, using this, for example, for successful sim-to-real transfer, and I will discuss this. And the second one is Safe Control Gym. It's a physics-based, again, gym environment. It has a quadrotor dynamics model, but it also, the motivation is that we add other dynamics models. And the key difference here is that we have symbolic a priori dynamics and symbolic constraints that you can define and therefore benchmark model-based and learning-based control as well as model-free reinforcement learning. So the motivation was really to compare and understand the differences between some of the model-based approaches and model-free reinforcement learning. And so this was motivated by a survey article that my team did, Safe Learning in Robotics, where we saw that the community is really divided into people in the reinforcement learning field and people in the classical control systems field. And we hope that this software benchmark can also bring these two communities closer together. This tool, a Safe Control Gym, was also used in our IROS 2022 competition and in a UAV control course, and both included going from the simulation to the real world, and did that successfully, and I'll show that. Maybe before I continue, maybe the team members who worked on this who are here right now, you can maybe briefly stand up. So Sikisu and Jacobo is here. So they were strong contributors to those toolboxes, and you can ask them more detailed questions as well later. So let's start. I first wanted to give you a brief overview of the three kind of different possibilities you have there. So it's gym-pybullet-drones, which we developed, Safe Control Gym, and Safe Control Gym with a sim-to-real in a sim-to-real branch, where we did some modifications to enable simulation to reality transfer. So what they all have in common, which is important for this workshop, is they have full physics-based dynamics equations of a quadrotor. Then the Safe Control Gym has also other systems, and we hope that the community continues to add other environments to this. What we have in the gym-pybullet-drones is we do have simple track, ground effect, and downwash models, and also a collision model. In the Safe Control Gym, because the motivation was to compare model-based and model-free approaches, we have the option to define symbolic models for dynamics and constraints, and also a very reliable and repetitive disturbance injection, so you can test for robustness. When we kind of expanded our Safe Control Gym to be sim-to-real capable, we also included, developed a Python wrapper for the firmware. And so all of those quadrotor simulators are actually based on the Crazyfly tool. And so these are the parameters that are by default there, which is also, you know, a very inexpensive and very reliable platform. But you can, of course, change the parameters such as mass and arm length and things like that, inertia, right? But that's the core parameters that we use. And that allow the sim-to-real transfer to the Crazyfly platform. And then for the inputs for sim-to-real, actually the work from Professor Diepol's group, which we are not involved, they even used the gym-pybullet-drone for sim-to-real, where they used motor command inputs, which is something I wouldn't have thought that this is possible, like going from the simulation with motor inputs to the real world, and it actually worked. But then they also compared it to attitude rates and attitude. So they did different studies. For our Python wrapper and the sim-to-real branch of Safe Control Gym, we have the standard crazy swarm interface with position, velocity, acceleration, and your rate. So that's the quick overview. Right, so all of them have the full physics-based dynamics equations, and that was important for us because, you know, in machine learning, often very simplified problems are considered that are far away from real-world robotics. So let me start with gym-pybullet-drones and give you a few more details. So the motivation was really that data sets and shared benchmarks really benefited the development of deep learning. right? That also included some developments around robotics, such as the KITTI data set for self-driving. But often in robotics, we still use simulators that are not easily integratable with machine learning flows, or we use toy problems in reinforcement learning environments that have very little to do with real robotics, right? So it's hard to do machine learning for realistic robotic systems. That was really the motivation to do this work. And the contributions of gym-pybullet-drones is it's a gym-compatible environment. So it has this interface that is then compatible with many open source reinforcement learning algorithms. And it enables then reinforcement learning of single or multi-agent quadrotor problems. The main features are it's realistic. It even enables sim-to-real transfer, as I mentioned. It's very flexible. It's computationally efficient, allows parallelism during the simulation of multiple drones, and is easy to use, which is also what the community, I guess, saw and therefore used. We compared in the paper that goes along with this software toolbox, we compared against the other kind of competing frameworks at the time. So that we released this 2021. So this was Flightmare, AirSim, and CrazyS. And the key difference, among others, is that we provide the interface to GYM also for the multi-agent case, right? And so the Microsoft AirSim looks like this, has a really nice visualization. And then Flightmare, we heard this before already. So this is really the key difference of this approach. But what is important to note as well is it's very computationally efficient. So you can either render the vision or not. Like if you not render it and you just fly one drone in one environment, you get a 60 times speed up compared to real time. So you run the simulation actually 16 times faster than real time. So you can do 16 times more experiments than you would be able on a real drone in real time, right? And why is that so important? Because we want to simulate many, many drones, and therefore, simulating a single one needs to be efficient. And so a single drone, with 240 Hertz physics updates, simulates 15 times faster. And then, another example is 80 drones for environments. It's roughly, in real time. So you can simulate 80 drones in real time without, losing time. So that was some of the main advantages. And here you see an example. You see multiple flying. We also implemented collision. So if things fall down, it looks like this. So this was gym-pybullet-drones, just a very quick overview. The key message is full quadrotor dynamics and compatibility with all the open source reinforcement learning libraries. And now I want to emphasize the difference and the motivation for safe control gym. So in a nutshell, what is safe control gym and why did we build that? So we were lacking in, when we looked at typical machine learning research, a lot of things are neglected. One is that we often have very useful prior knowledge in robotics that we should be able to be using if we do machine learning for robotics, and that data can be cost and or time expensive to collect, right? Furthermore, compared to the typical OpenAI gym environments, in real robotics, we have disturbances and noise, and they cannot be neglected. And finding reinforcement learning solutions or machine learning solutions in those simplified scenarios may not translate to the real world. And lastly, safety and constraint satisfaction is really important, right? And so that is also something we want to specify, that there's a gap and the robot should not fall down, for example, right? In the machine learning algorithm. And so that's why we created Safe Control Gym as a simulation environment with an emphasis on model-based control, that you can actually specify a model of your system, that you can learn uncertain dynamics, and you can also test for robustness and constraint satisfaction. And so we have different systems. As I said, right, we have the cart pole. We started actually initially with the 1D quadrotor and 2D quadrotor, so only moving in one, up and down, or only moving in a plane. But now we also have this 3D quadrotor. Why did we choose these? Actually, it was not that quadrotors was actually what we had in mind. We wanted to find simple systems that both communities have used in the past, like the reinforcement learning community and the control community, and such that hopefully both communities find this useful and and use it. So yeah, you can find it under our GitHub link. And so the key features that you have available is you can, in symbolic form, provide your model, like x dot is equal to fx comma u, right? So really in symbolic form, you can provide a model that you use then for control. And that model, may be similar or different from the real simulation, right? It may be an approximation, but you may still want to design your controller based on that model. It allows you to define safety constraints, such as the room boundaries, actuation constraints, obstacles, etc., also in a symbolic manner. And it has a reproducible disturbance injection, such that you can run different learning algorithms or different control algorithms under the same exact same disturbances. And you can have input disturbances, process noise, and additive dynamics uncertainty. And then it's compatible with a gym interface, such that you can use standard reinforcement learning algorithms that have been open sourced already. Right now, we have two main tasks: stabilization and tracking of a predetermined trajectory. And you can evaluate controllers based on those two tasks, but you can also expand on this and define a different task. So it is developed with pybullet for the dynamics, PyTorch and Cassidy for the symbolic representations. It supports a YAML-based configuration system for quick and reproducible experiments. And it expands the typical gym environments by the symbolic models, the constraint specification, and the disturbance injection. And so here you see a quick kind of drawing of the setup. So here on the controller side, that's really what we want you to explore, right? To explore different controllers, both learning-based and model-based approaches. And then, you send the actions to your simulator environment. And there we have the symbolic models that you can specify. And those models can be used in the controller design, if you have a model-based controller design. So those are an abstraction of the real physics that are defined in pybullet. And you have the block for dynamics disturbances, input disturbances, and estimation disturbances, and you can define those constraints. So we have a list of controllers implemented, which is hopefully very helpful, because if you develop something new, it should make it easy for you to compare to the state of the art in this field. And you can easily swap out here, controllers, and also work with existing frameworks such as stable baselines. So we hope that it really enables benchmarking of model-based and learning-based control and model-free reinforcement learning. And therefore, we implemented a number of controllers which you could all use if you compare your results against those. And those include the traditional, model-based control approaches like LQR and model predictive control, but also very standard reinforcement learning algorithms like PPO and SAC. And then we have also some of the more state-of-the-art safe learning algorithms, some robust RL algorithms, some safe reinforcement learning algorithms, and some algorithms that are more driven by the controls community, such as Gaussian process-based model predictive control and control barrier functions. So several are already published and several others are under works, but it helps you to really do comparisons in an efficient manner. And so here I show you just an example of how these results could look like. Let me explain it to you. So here we have a square, and think of those as the room boundaries, so your constraints. And the controller wants to follow this red circle, or the goal is to follow this red circle as closely as possible. And so we do different controllers here. One is a linear model predictive control using a linear approximation of the quadrodynamics and a slightly inaccurate model. And you see the robot, despite model predictive control being able to integrate those constraints into the design, right, and into the computation of the control input, it violates the safety constraints. But we integrate the symbolic representation of those constraints into the model predictive control formulation. So that's possible with this software framework. Then here we have a learning-based model predictive controller. So it learns the dynamics over time. And you see it satisfies the safety constraints. And the safety filter is an approach where you use a non-certified or non-safe reinforcement learning approach, and you add on top something that minimally modifies the input to keep the system safe and within the boundaries, and that does also reasonably well. So these type of comparisons you can do, right? This was still relatively simple, but still those comparisons were not possible before. And I show you one more result that you can do. So here we have 3 different control approaches. The first one is a learning-based model predictive control, where you learn that over time, the model of the system or the model error of the system. But you start with a prior model. And that prior model that we chose has parameters that are wrong by 150%. And the other 2 approaches are model-free reinforcement learning approaches, right? So they have no prior information. And so you see, and this is not perfectly tuned for being a perfectly fair comparison, but you get an idea what kind of results you can generate. So, with the prior model, even if it's pretty off from the real world, we start with a really relatively low error in our first trial, and then as we collect more training data, the performance gets better and better, right? And then if we have a model-free approach, we need already magnitudes of more data to really even safely complete the task. And then over time, you improve performance, but you see the magnitude of difference in the data you need, the performance difference. In this particular case, where we haven't perfectly tuned everything, in this particular case, in the end, the model-free reinforcement learning approach, the PPO is actually giving a bit better performance. The SAC is worse than the model-based approach. But these are the type of results you can get with this tool. So yeah. So to summarize, it's a software framework that has the gym interface, uses pybullet, pytorch, and Cassidy to define the dynamics and the symbolic representation and a YAML configuration system. And then the core features you have is that you can define symbolic models, constraints, and disturbances. And we have already a number of baseline implementations from traditional control to our reinforcement learning and safe learning-based control approaches. So once we had this developed, we also wanted it to be used by the community and also used in our courses. And so we were thinking about sim to real for this particular setup. And so what we did is we did a wrapper around a Python wrapper around the onboard controller software of the Crazy Fly and included that in our simulation, and that enabled sim to real transfer. And we did it in two different occasions. One was the IROS 22 competition, which is flying through a number of gates as quickly as possible, but there are dynamic disturbances and the gate positions may change and you have to react and adapt in real time. We also used it for a course. And so here are the links to the different branches. So right now there are still branches of Safe Control Gym. They're not yet merged back, but they are all available. And so here you see the setup that we had actually for the competition. So that was in simulation, and that was then in our lab in Toronto. And so in the next video, I show you how it a result from the course. So here, they only tested this in simulation and trained it in simulation. And now, okay, the Crazy Fly is small. I hope you see it. The drone is flying here through all the gates and actually succeeds. The next video is from the actual IROS competition. It's the result of the winning team. And so you see it first in simulation and then in the real world. And so the teams could only do the development and testing in simulation. And the top 3 teams from the simulation we took their code and actually tested it in our lab in Toronto. So they had no chance to do any improvements on the real system. And so here you see the simulation result of that team. Now you see it, here is the drone, again, pretty small, I hope you can see it, flying through the gates and successfully still completing the task in the real world. So yeah, so really the motivation for all this work on Safe Control Gym came from our review paper on safe learning in robotics, because we saw there's a huge trend, including work from our group, to advance the field of safe learning in robotics. But it was hard to compare and understand the differences of the different methods that were coming out. And that's why we generated Safe Control Gym. But we also continue to connect with the community. And if you want to see see all the resources that we have collected over the time, you can go to saferobotlearning.org. That webpage, for example, includes the details of the IROS competition. It also includes the talks and the workshops that we have been holding, both at NeurIPS, at robotics conferences, and also efforts in the controls community. So there's also a way to sign up to mailing list if you want to get a notification if we do another competition or another workshop. So overall, I showed you 2 kind of gym compatible simulation environments. These were our first kind of simulation environments that we actually open sourced. Both were motivated by the fact that we want to use machine learning and realistic robotic systems, right? And see and understand their performance. So what are some of the open questions still? Something we are interested in is how can we simulate sensor signals in cluttered environments? In particular, sensor signals such as the lighthouse system from BitCraze, ultra-wideband, which we use quite a bit in our group, and 6G. So different than the typical vision-based sensing. Can we provide guarantees for sim-to-real transfer? So we have some work actually by Siki where we explored the idea of bridging the model reality gap with an underlying adaptive controller that compensates for the difference between simulation and the real world. But that's definitely something that's also interesting for our group. How can we learn from real world data to improve the simulator? We have not done this in a very you know, if we have done it, it was in a very ad hoc manner. And then for fair comparison, similar to what I showed you for the safe control gym, we need to do a proper hyperparameter optimization for all the control and machine learning approaches, right? And so we are looking at hyperparameter optimization algorithms to include into safe control gym. To finish off, how do I see the role of simulation, right? So I think, you know, it's really incredibly important in order for us as roboticists to share our work in robotics, because, you know, what the simulation environment is in robotics is kind of the data set in machine learning, right? So in machine learning, it was much easier to share code and open source code because they only run on a data set in a feed forward manner, and there's no feedback. In control and decision making for robotics, we need simulation environments to help us share our work. It enables benchmarking in robotics, which is something we intend to do with Safe Control Gym. It accelerates development and deployment of algorithms in robotics. And one feature that not many may think of, especially not if you're a robotics researcher, I also believe it enables non-experts to program robots in the future. And we have done this very early on, where we wanted to have flying drones move in a choreography with music. And that was work during my PhD. And there our intention was that we had an interface where choreographers can design trajectories and see it in simulation, and so even though they are not roboticists, right? And I just show you a quick video kind of what that looked like. So there's actually music usually, but with the whole Zoom sharing, we'll keep it without the music, but it was actually music that was just generated for this demo. And so someone was in a very simple interface could choreograph something like this based on existing motion primitives and based on looking at the performance in simulation and checking that, you know, everything is okay, and also checking that it looks like they had intended. I also really think that in addition to sharing and comparing, simulations allow us really to push the algorithms to the limits, right? I mean, we don't necessarily want to do this on flying vehicles, but we can do and try in simulation. And when, if we see that it works in simulation, we can have some confidence that it may work in the real world. And so one work I wanted to show you was this, where we flew 25 drones. This is in real time. And so they always transition between different periodic patterns here. And there was, you know, lots of testing and simulation before you do that in the real world, of course. And this was also with a crazy fly. And finally, I also think this is incredibly important to enable work across continents, which is just very important right now for my group, where we have a team in Munich as well as in Toronto. And if you want to continue following our work, our tag is Learn This Lab. Thank you.
Questions for Angela?
Great work. So I have a question regarding the sim to real transfer. Which kind of control modality do you choose for the policy, like the neural network policy?
So are you talking about what we did for the competition, or are you talking about
just, in general, like for transferring the policy learned in simulation to the real world? What are the control modalities?
You mean the control
output, like is velocity command or is it position?
Yeah, it's position and velocity.
Okay.
Yeah, so velocity as a feed forward. Yeah, so it's quite high level. In that case, it was the first time we did it, and we did it right for a competition, and so we want it to work. But yeah, so I think, yeah, that was enough.
Thanks.
More questions?
And thank you for the presentation. The work looks amazing. I have one question. You presented 2 frameworks that are able to train reinforcement learning policies for quadcopters or for drones. So if I want to drive one policy, which one would I use? Because I mean, both are gym compatible. So if I want to train a reinforcement learning policy, which one would I use?
That's a very good question. Yeah, so just to make it clear, the pybullet-drones one was an earlier work, right? And the safe control gym is a newer work where we added some features such as the constraints and the symbolic model, but we haven't added the multi-agent capability. So if you have a single agent and you don't want to focus on safe learning, you could easily use the pybullet-drones, which is probably just a bit simpler because it has less features. If you want to kind of go in this direction of safe control or check if the constraints are eventually, at least after learning, satisfied, then safe control gym is a good choice. Yeah.
One last question.
Thank you for your talk. You've mentioned in your presentation about the physics-based model, and it enabled to also add some disturbances for robust control test. In what extent that this physics-based, like does it have like aerodynamic drags, and which wind can be added or disturbance can be added?
Yeah. So so for the pybullet-drones, we have simple ground effect and models and the collision models. We don't have complicated aerodynamic effects at all in neither of them. Then what disturbance can be added? That was your question. For that, you would use safe control gym, and there we have you could directly change the actuation signals. So basically, if you send a certain thrust to a motor, you may not get that thrust that you intended to have because maybe the propeller is a bit is more used or broken. And so you can model that. You can put force disturbances on it. You can have model errors. So full dynamics models that are.
How about the model? Can we modify the model, like add some aerodynamic?
The simulation model, it's all open source, right? So I hope it's readable and you can change anything. Yeah, absolutely. If you do that, consider merging it back into the main branch.
This one has so.
Yeah. Then think of test it and think of merging it back as an option of people, because we enable this possibility of model errors, and an aerodynamic effect would be like just an additional model. Yeah, for sure.
Okay, let's thank Angela one more time. And now we will have our poster session for about 45 minutes, and at 3:30 there will be also refreshments served outside. The posters are on both sides of the room, so please presenters be at your poster and everybody can walk around and interact.
Around here also. Yeah. So you don't have any problem like that. Okay.
These are my leaves for developers. We have to organize a meeting and discuss the moment. No, but I don't not fully understand how he works. So having someone that can answer some technical questions. Well, I mean, at the end of the day, there has to be someone that accepts or not. Yeah, you know, also you are the people who are more experienced. Yes, but it's better on the target.
Just a quick reminder, we will continue in about 2 minutes with our next talk.
I think that it's not done, or maybe it's done, but I don't know. A picture of the whole people like we have. It's not about saying it should be this way or not. Say is that it's super difficult to know which release match is, for example, now that BX like those two packages are aside from the actual BX4 thing, knowing which message version can be this release or this is super difficult. Yeah. Yeah, but our meaning is not just listening. It's not that we are the only users of it. So if someone has developed something, some constraints or something, and we make some changes, it has to be working for them. Yeah.
Thanks.
Jaeyoung. Yes. You can just call me PhD student. When I introduce, I'll just add the PhD part. Yeah, yeah.
Okay. That's it. We should start the second part of this workshop with the other two speakers. So please have a seat. Okay, so our next speaker is Jaeyoung Lim, a PhD student from ETH. He's gonna present simulating workflows for aerial robots with software in the loop.
Yeah, thanks for the introduction. So my name is Jaeyoung Lim. I'm a PhD student at the Autonomous Systems Lab, and I'm part of the PX4 core developer team maintaining the simulation component. And I'll be talking about simulating workflows for aerial robots with software in the loop simulations. So I guess the purpose of this workshop, we all know that simulations are very important for developing, especially aerial robots. It provides a safe environment for testing safety critical features that can be catastrophic for aerial robots. It also provides us a controlled environment where you can do repeatable tests and have access to ground truth, which is very useful for research. And mostly, it provides a way to maintain fast development cycles for experiments where we don't actually have to fix hardware or go to a flight test site. So a simulation is useful because it approximates reality. We have normally a real system where we put inputs in to do actuation or receive perception. But simulation is useful because we can focus on the parts we actually care about. So for example, if we're developing an attitude controller, we normally have a simulated model that has attitude dynamics, and then we see how it behaves with different methods, inputting range commands and observing the state response. And the typical development process of most researchers would be that you actually evaluate your method on a very simplified simulation model, and then you go out and re-implement your approach on a real system. But what if we actually want to test our software? So like our stuff is getting more and more autonomous. It's no longer just an attitude model. It starts to have its own mind, and we work with APIs now. And we want to receive perception data from the real system, and our software stack will generate some action commands to the vehicle. And the question is that how can we actually test this without actually trying it on a real vehicle, crashing it, fixing it again for the next 3 months, and then you haven't done any research done yet. So the way we can do it is that we can actually simulate all software interfaces. So for example, a real vehicle will have a Mavlink interface or a UAV CAN interface. And then we can actually simulate these interfaces in software because they are real software. And then we can actually and then they will have additional to the dynamics, maybe sensor models or actuation models, and we can test our software against it. And we can be very sure, because they use exactly the same interface, that they will also work on real models, on the real vehicle. So why do we care about software in the loop simulations? They are very useful for demonstrating behaviors because you are actually running the real software that runs on the real hardware. So you can actually demonstrate behaviors. If there's a software update, you can actually give it to an operator, make them test out the new behavior of the vehicle so that they are comfortable, they know what's going to happen when they fly the real vehicle. It's also useful for software testing, for example, in the PX4 Autopilot project, which I'll visit a bit later. If you make a code change, they would build the software, fly it in the continuous integration pipeline on all vehicle targets, all supported vehicle targets and configurations, and do end-to-end testing so that they make sure that you actually didn't introduce any regressions on the whole software. So you can see all the sensors are all simulated. It normally runs in real time, 40 times real time, considering that the IMU frequency is 250 Hertz. The simulation frequency is quite high. And lastly, as mentioned before, you increase the development cycle where you don't need to actually go out flight testing hours and hours, maybe like this flight test I did beginning of May. We had to hike up with the plane for 1 hour in the Swiss Alps. And then it would have been a very big disappointment if we found out that we didn't do something right and then had to come back to the lab. So in this talk, I would like to focus a bit more on how you can actually simulate these workflows in the software-in-the-loop simulation, how you can create your vehicle models, and then lastly, a bit work in progress, how you can calibrate these simulations. So in case someone is not familiar with the PX4 project, PX4 is an open source flight control software for drones and other unmanned vehicles. And a lot of developers or researchers use it since it's open source. It's hosted under the Drone Code Foundation, part of the Linux Foundation. So you can be sure that it won't be meddled with other people. And then it has a very modular architecture and it's very configurable. So you can have very special research use cases very easily supported using this firmware. PX4 is a software, so it can be run on hardware that supports the Pixhawk open hardware standard, which is manufactured by various manufacturers. They have very specialized hardware for different use cases. For example, on the left is kind of for a very small 5-inch racing quad. And then on the right, you see something closer to an industrial drone use case with built-in autonomy. And PX4 is not actually for hobbyists or somebody in a dark room having fun with drones. It's actually being heavily used in the industry. So these are some of the examples that are either compatible with PX4 or actually use PX4 in the industrial use case. And personally, I quite like the fact that if you're developing something that's really getting used and you can understand what the actual people in the field struggle with in terms of autonomy or use cases. So how can we simulate workflow? So I normally say we should not only simulate dynamics, but simulate the whole workflow in software-in-the-loop simulations. So this is a good example of how you can actually simulate the full end-to-end workflow. All the sensors and payloads are being simulated in real time. And the ground control station actually doesn't know whether the vehicle is a real vehicle or a simulated vehicle, because the data that comes in and out of the simulation are identical to the real vehicle. And this is quite useful for testing or getting used to what the vehicle behavior would be on your implementation. And also for someone maybe developing something more closer to the ground control station or high level things, you are very sure that it will also work on the real vehicle if it works in software-in-the-loop simulations. So PX4 is a sort of a middleware. It has a pops up messaging bus called, the message is called UORB, where the different modules of the flight stack talk to each other through this message bus. So it's a very modular system where you can just swap out the modules, and there's a misconception that people try to use PX4 as a black box. It is not, compared to other autopilots where it's a monolithic code. PX4 is more closer to what you think as ROS or ROS2, where you can publish messages and each individual module doesn't know actually where the data comes from. One really cool thing combined with this is that PX4 is POSIX compatible. So it means that you can actually run the code that you're going to flash on the microcontroller on your laptop. So as long as the data the workflow is similar to the real vehicle, you can actually test everything that's going to run on the microcontroller that has very different computational powers on your laptop. Until now, the simulation architecture looked like this, where the PX4 instance or soft in the loop simulation will talk to the simulation through a Mavlink message called the Mavlink Hill message interface. So it will send actuation commands to the simulation. It will progress one step, and then as a feedback, it will provide perception or like sensor data, and then it will create this loop of the simulation and the flight stack being synchronized. This is quite nice because it can be naturally extended to HITL, harder in the loop simulations. But since Mavlink itself is a standard interface, unless you're using the predefined use cases, it's very hard to expand. Because it's a standard, it's very hard to introduce new changes to the message definition. So now we have we're moving away from this architecture. Now we have a gazebo bridge module, which actually talks ignition transport directly. So you can have much more flexibility on how you interact with the simulation, because the PX4 is kind of tightly integrated in the simulation itself. And also, there is no longer a special module that packages data and then communicates to different plugins. You can just interact with different plugins with different namespaces naturally through ignition transport. One more thing is that we now have a standalone sensor simulation. So normally IMU can be quite high rate if you're trying to simulate real sensor rates. And this, if you use the Mavlink lockstep integration, is one of the limiting factors of using more high-end photorealistic simulations. For example, X-plane or more advanced flight dynamic simulators would use physics integration in rendering rate, which is too slow for drones in terms of dynamics or sensor models. And as you can see, you can now start to abstract this dotted orange line as one vehicle, including the flight controller and the simulated hardware. And we can start thinking about really integrating autonomy. So a good example would be, there would be a mission controller on the vehicle, and it will be it will be some autonomy function with maybe ROS2. And then now we have the ICRA XRC DDS bridge, so that can actually directly talk to UART messages. So now we don't have any repackaging or serializing, deserializing bottlenecks in between. We can actually start to talk naturally through UART. So PX4 becomes kind of part of UART. You can have a distributed system. For example, you can replace the low-level rate control module to a more advanced MPC module that runs on the mission computer. And the rest of the system would just work because the individual module wouldn't know the module was actually swapped as long as the data is similar. So you can actually, because this is all abstracted out from the mission computer side, you can actually be quite confident that if you had something working in the software in the loop simulation, it is going to work on the real vehicle. This is just a simple example from my research where I tested a fixed wing path planning module running in software in the loop. And this was quite useful because you're out in the field, you're flying long distances, and it's not just kind of the logic or algorithm that matters, it's the real workflow that you need to simulate. What if there's too much wind? What if there's a fail-safe? What if it lost RC? What is the action I need to take to safely execute the experiment? So you can really practice some operational routines and make sure that your experiments are going to be safe. So we now know how to simulate sort of our end-to-end workflows, but how do we come up with the vehicle model itself? So we'll first talk about sort of the configurations of the vehicle, how we actually simulate environmental effects. And then lastly, one of the biggest problem with sort of outdoor flying vehicle is to actually accurately simulate the aerodynamics. So as you're already quite used to, vehicle configurations are defined through a kinematic chain, basically a SDF file, or some other configuration file for other simulators. And there are basically two actuators, motors and servos, where motors are velocity controlled actuators and servos that are position controlled, so which can be applied to control surfaces or maybe something like a gimbal. And there are also an addition of aerodynamics, where this is kind of a passive actuator that can be influenced by these position controlled actuators. Also sensors such as IMU, GPS, airspeed sensors, or LiDARs, or any other sensors that can be simulated in the simulator can be added to the vehicle. And as you can see, we can start simulating very complex vehicle configurations like a fully actuated omnicopter or a VTOL, a tilt rotor VTOL vehicle that can transition. To simulate environmental effects, we have sort of a wind world plugin, which is situated in the world, where it generates wind velocity messages. And this wind velocity message gets incorporated in all of the actuators and aerodynamics, where it influences for the motor plugin, the advance ratio and maybe drag. And for the airspeed sensor or aerodynamics, it changes the air relative velocity. So you can actually start simulating quite accurate behaviors of what will happen if you have wind during your flight test, which if you're flying outdoors is most of the case, you will always have some sort of wind. So this is a demonstration of a soft-in-the-loop simulation in a windy environment. This is a fixed-wing environment. You can see that the vehicle is trying to maintain airspeed, but the ground speed fluctuates up and down in a symmetric manner while the vehicle is flying in a circle. To model the aerodynamics, Gazebo uses a linear aerodynamics model. This is the default lift drag plugin you see. In PX4, it's slightly modified to incorporate a bit more advanced control compatibility and wind. And it consists of multiple components, which if you have body rates on your vehicle will sort of influence the angle of attack of the lift drag component and will generate force. So you see there's multiple components that generate different lift drag depending on the control surface positions. And each wing section will basically be a single lift drag element. However, this normally it's very hard to tune and make realistic on your vehicle because you don't know exactly where the center of pressure is on your vehicle. So Karthik from Kidiok has contributed a advanced lift drag plugin where you can actually simulate aerodynamics as a lump sum model. It has much more parameters. It's 36 for the base aerodynamics model and 6 for each of the control surfaces. And the post dynamics is approximated as a flat plate model. You can basically simulate very sophisticated aerodynamics because the parameters actually come from an AVL. So since we can create these very accurate vehicle configuration, we can start testing end-to-end functionalities. Maybe one of the good demonstrations would be that functionalities related to wind. So you can see there's a functionality called weather veining, where the vehicle is supposed to point, vertical takeoff and landing vehicles are supposed to point towards the wind direction to minimize the frontal area during hover. And you can see, you can successfully demonstrate these functionalities. And really the workflow would be that you observe something on a real hardware, you want to replicate it on a real vehicle, you see if you can reproduce issues or problems you found on a real vehicle, and that's how you can make your simulation more and more accurate. So this is a bit ongoing work on my side on how we can now create the structure of the model the vehicle model accurately, as long as we have the parameters. But it's often the case that we have some prior knowledge of the vehicle, but we don't know everything about the vehicle. But in simulation, you actually need to tell the simulation everything in order to simulate it accurately. So normally what happens is people make some assumptions, they make some model structures, they put it in simulation and integrate it as a realistic vehicle and try to put parameters in the actuator and sensor models. It flies okay. Then they go out and fly the real vehicle. And then you find out that sort of the real flight data doesn't actually match what the simulation is doing. And this is probably because of the discrepancy of your prior knowledge or holes in your knowledge that are causing this. So we need to actually be able to feed back real data to make the simulation model better and better, and to calibrate the simulation to match reality. So with Manuel, our previous master student, we created a framework called Data-Driven Dynamics, where we try to do system identification directly from flight logs. So with small UAS especially, is that when the vehicle is developed, it's very rare that the vehicle goes through a full system identification campaign or wind tunnel testing, but the vehicle already flies. So we can actually utilize this situation by processing the flight logs and convert it to a vehicle dynamics model and try to identify the model parameters from the data. And we quickly learned that in order to do this, the results are very sensitive to the data you provide to the pipeline. So there is also sort of these interactively tools to interactively curate the data, or if you're doing a specialized maneuver, you can put it on a manual switch and then tell the pipeline that you are doing an identification maneuver. The pipeline will only use that part of the log. So this is a demonstration of a identified quadcopter model flying in a software-in-the-loop simulation. So the vehicle is kind of modeled as a lump sum model. You can see the propellers not spinning. This is for demonstration purposes, that it's not actually using the gazebo motor model, but a identifies force model. And you can see that the vehicle flies. Quadcopters are quite easy to identify because the model parameters are mostly observable in almost all state of the flights, but this can get a bit tricky with fixed wings or VTOL vehicles, where depending on the flight state, some actuators might get actuated or not actuated. So with Pascal, we try to look into how we can identify sort of the information quantity inside the data logs. And you quickly see that if you get operation flight logs from vehicles, most of the flight logs are actually not informative. They are quite redundant. For example, if it's a fixed wing or a multicopter, most of the flight time is spent in hover, which doesn't provide us any more data. So we looked into how we can actually utilize sort of this information theoretic measures such as fish information to decide whether there is enough data in the flight log, or how you can quantify the uncertainty of the model from the flight log directly. We try to close a loop on trying to not only just simulate the vehicle, but see if we can use this for trimming or auto-tuning the vehicle. So with Julius, our previous master student, we created this pipeline as part of the data-driven dynamics pipeline, where it can process flight logs, run system identification. It will actually output parameters that are relevant for controller tuning. And we could see that, so we did the test on a tilt rotor VTOL. This is the model fit of the prediction of the flight log. And we could see that the sort of trim values fit quite nicely. So you can see here that for a certain airspeed, for the trim value, we identified the sort of elevator input, which is additional to the trim value, is almost 0, which means it fits quite well. It was a nice surprise where I would have never thought the vehicle was this nose heavy, but apparently this is the correct trim value for the vehicle, which just shows that it was sort of poorly built, but a nice discovery that the pipeline is actually working. We can also see that the model fit is not that good in other airspeeds, which means that our model is maybe not good enough to extrapolate to different airspeeds. And this is part of the problem where we have this issue where we might get data in some parts of the flight state spaces that fit, but maybe we have a wrong model structure. For example, for this work, we used a linear lift drag curve just for convenience and also for observability issues where you actually need to stall the vehicle if you try to get data in identify the stall parameters. And you can see that because we are making this sort of structure, model structure assumption that the model is not fitting the prediction. So I think this would be sort of our outlook on how we can handle this kind of uncertainties on the model structure itself, or how we can handle the residuals of the model. So in summary, we looked into how we can actually simulate workflows and with software-in-the-loop simulations. We looked into briefly how we can model the vehicles and how we can actually calibrate the vehicle simulation model by identifying the models from flight logs. And lastly, before I close the talk, this is a short advertisement from the Drone Code Foundation, where there's a PX4 Dev Summit happening soon. There's also scholarships or travel funds that would be provided for students. And personally, it's very nice to sort of talk about sort of what's missing in terms of infrastructure. I don't see PX4 as something that is very influential for work, but actually infrastructure that you can utilize. So you shouldn't try to work around the infrastructure, but this is an open source project. It's not governed by a single organization. So we should maybe try to work together and try to get the sort of infrastructure correct and easy to use for researchers so we can enable each other. So yeah, so we support various simulations for different use cases. But yeah, hopefully we can try to make our lives easier, trying to simulate, making the transition between the simulated vehicle and the real vehicle so that we can focus more on our research. Thank you very much.
Any questions?
Hello. Hey, thanks for the talk. That was really interesting. I was just wondering if you could talk a bit more about how you simulate other sensors that aren't part of the PX4. So for example, if you had other vision sensors where you might have camera drivers that you want to test as part of your software in the loop.
So that's actually a very good point. That's partly what the sort of testing infrastructure is struggling with, because GPUs are quite expensive to run on the cloud. So currently we simulate optical flow and LiDAR, LiDAR not meaning a 2D LiDAR, but the distance sensor like a 1D LiDAR as a mock plugin. So we assume there's a flat plane and then we can just numerically test the sensors a bit more simpler, but it's definitely something very basic and we can get away with until now, but we would like to be able to test more sophisticated vision algorithms in the future. And that's partly why I think a lot of researchers struggle to set up a vision estimation pipeline with PX4 because there's not that sophisticated testing infrastructure built in yet. So it's people all do very different things. The interface is not clearly defined because it's not tested. And yeah.
Cool, thank you.
More questions? Okay, so then let's thank the speaker again.
Thank you very much.
Also, there are chairs if you want. You can come and sit in front.
Yes.
Okay, you introduce you. Let me introduce. It's my pleasure to introduce our next speaker. He's a professor at the University of Zurich, Davide Scaramuzza. And
thank you, Chiara. So this talk is going to be given by myself and Leonard, who is a doctoral student in my lab. So I will give the introduction, and then he would delve into the details of our simulation framework. The title of our talk is Vision-Based Agile Flight from Simulation to Reality. So we have been working on a vision-based navigation now for quite many years, more than 10 years. And we can say that the estimation is now quite mature under certain conditions. So we can find vision-based navigation on different commercial products. First of all, the Ingenuity Mars helicopter. It's been using now vision-based navigation in more than 50 autonomous flights on Mars. Here you can see Skydio drones doing bridge inspections with even more than 6 cameras. In the middle, you can see vision-based drones from Verity, based in Zurich, that uses drones for inventory management, so and barcode scanning. On the right, you can see swing drones doing precision agriculture and crop spraying using vision-based navigation. So what we can basically agree, I think, is that thanks to perception, drones are actually becoming more autonomous. But as you can see, human pilots are still the preferred tool to operate these drones in most of the applications. I would say that 99% of the drones, or commercial drones, are still operated by human pilots or otherwise by GPS. And the reason for that is that the current drones are still far from human pilot performance regarding agility, versatility, and robustness. Agility means you want to make the drone more agile in order to be more productive. Exactly what Mark Rybert said yesterday in his talk. That's why they want to make Atlas more agile. Versatility means that the drone should be able to generalize to multiple tasks. And at the moment, we have robots that can only solve a single task very well, but not multiple tasks. And robustness means that they should never fail, ideally. Now, what would be the benchmark for navigation? What would be the best pilot for vision-based navigation? The human, of course. Human pilots can train themselves to become so skilled in actually up to several years. So how do humans pilot drones? They pilot drones vision-based. There is a camera on board the drone that relays the images to goggles, and then the human brain processes this information and sends it to your fingers. At the beginning, when we started working on agile autonomous vision-based flight, we thought that the reason why humans are better than machines is because they are faster, and we were wrong. So we published a paper where we tried to measure the reaction time of human pilots, and we measured it at a quarter of a second. Actually, precisely, we measured it at 220 milliseconds. So it's the time that takes a human pilot to react to a visual stimulus and until you send the control commands on the joystick. So the real reason why humans are better than machines is not because they're faster, because actually they are slower. Consider that our algorithms are 10 times faster than a human making decisions. But the reason why humans are better than machines is because they can make better decisions in complex situations, which is basically the same that also self-driving cars researchers have been advocating. Now, what we are trying to work on in my lab is trying to crack the brain code, try to understand what it takes to fly autonomous drones as agile or even more agile than human pilots, ideally. Why do we bother about making drones more agile? Because if you can make a drone more agile, you can make it more productive. And we actually measured it. Actually, Leonard did it. So Leonard is the first author of the paper that we published at RAL last year. The key limiting factor of autonomy at the moment of drones is the battery time. It lasts for multicopters only 30 minutes, and it hasn't improved much over the past 10 years. So that means that if you want to make the drone more productive, so more useful for your task, you actually should fly it faster. We actually quantified it. Leonard quantified it. So what you can see here is the a plot that visualizes the distance covered by a drone in kilometers until the battery completely dies as a function of the translational speed. So what you observe is that, of course, when the drone hovers, so at 0 meters per second, it covers no distances. Then when the drone starts increasing its linear speed, also the amount of kilometers that it can cover before the battery dies increases. But it only increases up to an optimal speed, which depends on the quadrotor, on its mass, on the aerodynamics, and several factors, which are also commented in the paper. And what happens is that you can see that after this optimal speed, it's no longer convenient to fly faster. Why? Because you start consuming more energy, and you also start encountering more air drag. But there exists this optimal speed, which is actually not negligible. For the average DJI Mavic drone is around 6 meters per second, almost 20 kilometers per hour. How fast are current commercial drones? There. Here you have the world leaders in different applications, including inspection, DJI, flyability, Skydio. As you can see, well, we know they are capable of flying much faster, but they are not taking full advantage of their potential. Why? Because when you try to fly agilely, there are multiple challenges that we will discuss. Another reason why, of course, you want to fly faster to cover longer distances is because by increasing the productivity of the drone, you will be able to solve a lot of tasks that matter to us today, such as rescue, exploration, personal air vehicles. In the Olympic Games next year in Paris, Volocopter, a German company, will fly rich customers from Charles de Gaulle Airport to the downtown Paris. So it would be quite interesting. And also NASA plans to send a hexacopter to Mars by 2030, and it's supposed to fly 10 kilometers. To do so, it will actually have to fly faster than Ingenuity. Another reason why us researchers are interested in Agile Flight is because it allows us to work on intellectually challenging problems, like, for example, perception, planning, learning, and control. And especially for computer vision researchers, it allows us to push the limits of vision-based navigation. So I hope I convince you that it's quite exciting to work on vision-based Agile Flight. How do you control typically drones? Well, we are all familiar with the classic control architecture of perception, planning, and control. So let's agree on this. Now, for drones, typically, you need to estimate the state, and it's part of the perception module. The state for a drone is not just the position and the orientation, but also the velocity. And second of all, perception is in charge of building a local 3D map of the surrounding of the robot. Then what you do is that you send these intermediate representations to the planning module that will ideally compute in a collision-free trajectory, and then you feed this trajectory to the control module that is in charge of computing the rotor speeds of the 4 motors. The problem with the current control architecture is that it's unsuitable for very agile flight. Why? Because when you start flying fast, first of all, you have perception noise. I would say calling it noise is not enough. Motion blur is more than noise. It's integration over time. And the interesting thing to say is that the perception, motion blur depends also on the trajectory. So you can actually choose trajectories that reduce or alleviate the motion blur by basically doing perception-based trajectory planning. Also, another problem with Agile Flight is that the quick rotations of the camera will cause deterioration of the image due especially to the exposure time. So you will have what we call high dynamic changes of illuminations. So some areas of the image will be underexposed or overexposed. And third of all, aerodynamic effects, especially in Agile Flight, you tend to fly in your own downwash. So you will actually have to handle turbulent flow, very turbulent flow. That is very difficult to model unless you use computational fluid dynamics simulators. Of course, you can do it, but they may take several hours to days, depending on the complexity of the environment and of the trajectory, and they are trajectory dependent. So if you want to integrate them into your training process, well, forget to have something that, converges within a couple of weeks. What would be the alternative solution? Do exactly what humans do, a single neural network that maps directly control commands to, maps directly sensory observations to control commands. We know one day will be possible because we humans are the living proof, but you know that it's very sample inefficient. So you will probably need billions or even trillions of images. And second of all, even if you succeed, it will have a limited interpretability. So what we've been working on over the past 7 years is on trying to get as close as possible to the performance of human pilots. And we've chosen 2 tasks that are quite difficult. Let me show you the first one. The first one is drone racing. So we have been working on this for 7 years, so I will not bother you with all the details that we're presenting over the past 7 years, but I can tell you that last summer we organized the first AI versus human drone race. The AI drone will be colored in blue, and the best human pilot is colored in red. The results and the whole description of the system will be out by August. So here is the title of the paper. And we achieved this not through optimal control. We have a lot of papers using optimal control, in particular MPC, MPCC, differential flattened base control with ANDI or not, but we realized that we're always underperforming with respect to the human. Why? Because they are too much limited by the reference trajectory. And also without domain randomization, they cannot cope with the varying state uncertainty, which is actually a problem in vision-based navigation. So we had to resort to a neural network controller trained with reinforcement learning in simulation with some fine-tuning in the real world that also Leonard will comment about. So let me show you a video. Let's see how it performs on Zoom. Okay, so the 2 drones are flying up with speeds up to 80 kilometers per hour. The maximum speed depends on the drone and on the trajectory. And one is ahead of the other one. I let you guess which one it is. And the AI drone is using only a single onboard camera and an onboard computer. The 2 drones are identical. The human piloted drone is a perfect replica of the human piloted drone, with a ballast weight to match exactly the same weight. And also the envelopes are the same to have the same aerodynamics. As you can see here, the AI drone won, and this was thanks to reinforcement learning. Another thing I've been working on is navigation in the wild, which means in unknown environments. For example, here you see our drone flying vision-based in an unknown forest, so trying to find a collision-free trajectories by mapping directly images to control commands. And also here, we have a neural network controller that was trained entirely in simulation. The reason why we use the neural network controller is because we show in the paper it's more robust to sensor noise, and it's also faster, actually up to 2 times faster than model-based approaches. And it also has 6 times lower latencies than model-based approaches. Now, how did we manage to go to do the training? We did it in simulation. So on the left, you will see the video that will be out when the paper is out, how we train the RL approach entirely in simulation using our simulator called Flymer. So we actually simulate 100 drones in parallel that basically learn to fly using model-free deep reinforcement learning. At the beginning, they don't know how to fly, so they start hovering. And then suddenly they start discovering trajectories, and they know that they have to maximize the reward, which is passing through a sequence of gates, and they are penalized when they actually bump into the gates. They also get a reward if they orient the camera towards the next visible gate. On the right, you see how we are instead training the navigation in the wild policy. That one is not trained via reinforcement learning, but actually via imitation learning, in particular privileged imitation learning, where we try to imitate an artificial expert. Now, Leonard will give you all the details.
So thanks, Davide, for the nice introduction of the topic on vision-based flight, on Agile Flight, and I hope it got you curious to know a bit more about how this is actually done. So let me go to the second part of the talk, simulation, but how? When we look at simulation, there's 2 possible applications. We could use simulation primarily for validation, or we can use simulation for training. And it is a very natural thing to think simulation must be as accurate as possible. How accurate can the models possibly be? And this would be the for validation side. However, for training, you will quickly discover if you work in the field that accuracy is not the only thing that matters. For training, it is actually much more important to be able to collect samples efficiently, because model-free reinforcement learning is known to be not very sample efficient. So there we also have a bit of a speed versus accuracy trade-off, because if we can collect samples faster, we can collect more samples. So maybe we get away with less quality of the samples themselves. So let me start with this side and have a look at the training side of things, or modeling for reinforcement learning. So what you see on the right side is a very similar animation to what Davide has shown before in the first half. And you see the drones really start to figure out quickly how to fly through the track, how to raise efficiently. And this is all done with a very simplistic model. So we only assume that the thrust and the torque that the propeller produces is proportional to the square of its rotational speed. This allows us to train extremely fast. We talk about 20,000 times real time or so, without the neural network backpropagation steps, but just the pure dynamics forward simulation is extremely fast. Now, the problem is, of course, such a model has inaccuracies. And if we want to zero-shot transfer it to the real world, this will not work because the real drones, as we've seen the talk before, have different characteristics. There are aerodynamic effects that you cannot capture with such a very simple model. So what we do here is we randomize what we cannot model. Domain randomization in this case proves to be very efficient. We talk about plus 20% of the mass, minus 20% inertia. So we produce a randomized set of drones, and the controller that we learn must be able to cope with all the varying dynamics. Heavier drones, larger drones, more delay in the system, less delay in the system, etc. And this actually makes it possible to transfer a policy that has been trained through this way, zero shot, to the real world. You put the drone in the Viking arena and you fly it, and it will fly. And it will fly faster than any human can fly because the controller are really time optimal by now. But this is only one side of it. Well, it allows you to come up with policies that are really fast to race in the real world. There's still much to be discovered. For example, what if we don't want to use reinforcement learning for our policy? What if we just want to validate that our approach works? What if we want to use simulation to optimize design parameters of a drone to maximize range or endurance? In these cases, and I personally believe they are the more interesting cases from a modeling point of view, in these cases, we cannot just use a simple, inaccurate model. No, we need quite the opposite. We need highly accurate models, and we also need to have the ability to really simulate all the parts of the drone as well, the controller. Ideally, we run our simulator in the same software stack that is actually deployed in the real world on the drone, because that guarantees that all the components are the same and that we do not have unnecessary drone crashes because our software architecture changed slightly. As the talk before already mentioned, aerodynamic effects are probably the hardest thing to model. And I want to pick up on this because drones have a wonderful advantage here. You can fly them quite easily in confined space with a motion tracking system because they're not huge fixed wing aircraft. So what if we kind of come up with a model that is a mixture of a classic first principles model and a data-driven model that we identify by flying a lot in a hangar and augmented system and measure the forces and torques? This was the approach that we've done in the NeuroBM paper, which happened to be my master thesis at the lab. So that was kind of my entrance to this world of agile vision-based flight. And the idea here is that you can use a first principles model and then augment it with a learning-based component. And then in the end, these two models together produce the forces and torques that act on the quadrotor based on its current state. This makes it possible to really capture difficult to model aerodynamic effects, as you will see on the video on the right. So here we have smoke, another drone flies through. And you can really see the vortices that are created by the drone passing. All these effects, highly dynamic, time varying, etc., cannot be captured with the first principles model, but a neural network learns that quite easily. So this improves the physics, the realism of the simulation by up to 60%. Now, if we need to go one step further, we realize a drone is more than an aerodynamics thing. A drone has more components. A drone has a motor, a drone has a battery. And following the success story of NeuroBM in terms of modeling accuracy, we also follow gray box modeling approaches for these components. Motor models, we've measured dozens of them on motor test stands and annoyed everyone at the lab with the horrible noise of motors and propellers. But motor models can also be identified from real-world data, time constants, the efficiency curves, etc. The same holds true for batteries. Batteries are inherently hard to model because you would have to do molecular chemistry simulations to really get the chemistry that's happening. But we don't need that. It is enough to represent a drone, a battery, as a voltage source, two resistors, and a capacitor. This model is fine-grained enough for our approach, and it still allows us to simulate things efficiently without waiting days or even years for the full model to solve. If you're curious and you want to find out more about this, go to this webpage. It's all open source. You can download it. Agilicious is basically our simulator control stack, all in one thing that implements what I've just discussed. We have different controllers. We have different models, and it's all integrated in one pipeline. But there's more to it. Even with the perfect dynamics model, we cannot model everything. So what you see here is actually a comparison of a real-world rollout in orange and then a simulation rollout here. Yes, they are very close to each other, and by very close, I mean less than 30 centimeters apart for most places of the tracks, but they're still not perfectly on top of each other. So what if we even need to go more detailed? Or in other words, how do we deal with effects that we basically cannot model? The perception system, for example, in vision-based flight is one of these components, or even the structural integrity of the drone. And with that, I do not mean crashing it, but I mean more things move when you fly so fast with 5 Gs in a turn. The camera moves, the battery moves, etc. How can we model these effects without using finite element methods or computational fluid dynamics? And again, neural networks come to the rescue here. So our idea is that we can actually fine-tune from real-world data. This is kind of a sim-to-real to sim-to-real approach. So you train in the simulation, and you can use even a simplistic simulation here with reinforcement learning really fast to get a good behavior of the policy. Then you deploy this policy in a motion capture system, and you try to identify the residuals. You try to identify what effects did you not properly model with your simplistic model. Now, these residuals, they depend on many things: the track that you fly, the current state, even the environment. Is it a hot day? Is it a cold day? Is it bright outside? Is it dark outside for the perception system? We try to identify these residuals and then adapt our simulation by including knowledge from these real-world rollouts and then fine-tune again. This system makes it possible to get policies that are extremely accurate, and you can really get it dialed into the performance that you require to compete with the world's best pilots, because they are good, so you need to be better. This approach makes it possible. Are there other ways? Well, you could also follow a slightly different route, especially if you don't need to train policies here, but if it is more about a validation task. And the last thing that we have from validation here is hardware in the loop. Fortunately, the flight stack that you can also download even supports that. So what you can do here is you have a platform flying in the real world with its real sensors, perception system. It perceives the real world. But then you can, for example, simulate gate overlays like here. Real arena, no gate. Our virtual arena has the obstacles. So you can test your obstacle avoidance algorithm without constantly wrecking the drone. This is really good as a PhD student because you don't spend all the time fixing it. How performant is it? Well, we have delays between 5 and 25 milliseconds. Kind of depends on the resolution and your exact components that you use. But it's a really good approach to use this in the real world. And you can kind of see this here. We can even simulate a different environment. There's the drone flying in the real world, and there's what it sees, what each perception system sees. You can simulate a disaster zone without actually wrecking an arena just because you want to simulate an earthquake. All of that is possible by just simulating it and accessing a wide variety of environments that you can download from the World Wide Web. So with this, let's summarize a bit what we can do. What is the role of simulation for us? So primarily the role is threefold. We can do it validation, we can do hardware in the loop, and we can do training. And we have different works, and this can be comparison of controllers where it's a more validation task to make sure the controller actually flies before you deploy it. We do agile flight in cluttered environment where we use hardware in the loop to not constantly crash into obstacles. We use validation to really optimize design parameters of a drone to understand how far it can fly and what its optimal speed would be to achieve that range. Or we use vision-based, we use training to train policies that can do vision-based aerobatic flight. And just because the video hasn't appeared so far, I want to highlight this one. So this is even outdoors, and the drone is doing loopings and can different maneuvers. And on the left, you can kind of see on what it was trained. So a lot of different environments, a lot of different cases. But once again, having access to an accurate simulation that is fast enough to train the policy in was the key enabler that really helped us here. And I mean, you've seen this now a couple of times to appear. So what exactly is going to appear very soon? Well, we've raised the world's best pilots, and we will share the insights with the community, what we've learned from that experience, what the pilots can probably also learn from us. because it is not just a one-way process. The AI knows things that humans don't know. The AI can optimize parameters that the humans never thought about. And the key point here is to do racing against the best pilots, you need to have the best simulation possible. But the best simulation isn't obtained by doing computational fluid dynamics because that is too slow. The best simulation is obtained by taking real-world information into your simulation in a fine-tuning step for the policy, and therefore really getting the dynamics right for the specific case to optimize for the performance. So let me conclude this by mentioning a few, well, open challenges, partially addressed challenges, things that we work on, things that you might work on. So for state-based dynamic simulation, a lot of things are already possible. You can use reinforcement learning, you can use imitation learning, or so you can kind of fit residual models to things. This is doable. If you don't want to use high fidelity model, you can really go for low fidelity domain randomization, good for training pipelines. You can go for data-driven modeling if you really need the high fidelity. These things are already possible. What is really the interesting part, what really makes drones versatile, is the perception part. And this is where probably the most open challenges are at the moment, also from a simulation point of view. Yes, we can simulate motion blur and high dynamic range scenes in Blender, ray tracing simulations, etc. But once again, it's computationally not tractable. It is not efficient. What we really need is an efficient way to simulate these. And Habitat Sim, a great project, also Unreal Engine and derivatives, AirSim, etc., are really a right step in this direction to address this. How can we move forward in terms of vision-based simulation? How can we adapt our simulators to be useful for vision-based Agile Flight and not just for a setting where you have a Vicam system that provides a ground truth state estimate? And I personally believe from experience now at the lab that this last point is really important. Integrating the simulation into the flight stack benefits you a lot. You get rid of the standalone concept of, oh, I have to test my setup in Gazebo, in something else. Now you tightly integrate everything and you run the same components. You run the same ROS node, whether it ends up in simulation or in the real world. If all of this is integrated in the RL pipeline, in the flight stack, you really benefit from that. And you're really able to develop much faster, much more versatile algorithms. Feel free to scan the link if you want to check it out. And with that, thanks a lot. Thanks to David for giving half of the speech to me. And now we are open for questions.
Any questions?
Thank you very much. Very nice presentation. So I was wondering, I think it's really smart, this idea of improving the simulation using real data. Did you encounter, however, the problem of getting enough data, especially exploring the huge state and input dimension?
So you're referring to the sim to real approach, kind of to really get the maximum performance out of it, I guess, like this? Okay. So for this, you don't need to explore too much. The idea here is that you already have a policy trained in the first step that is relatively good at the task. So it already knows kind of how to fly around. That means if you now record only a few laps of this and you assume that the distribution will not change too much between the two rollouts, and we've done like multiple, like sim to real to sim to real to sim to real and so on, it turns out you just need to do one of these iterations, then you're pretty much fine, because the behavioral changes in terms of the state space that is explored is very minimal. It is more the effect that the drone maybe coordinates the turn a bit better, brakes a bit later, brakes a bit earlier. But this does not lead to a large new state space being explored. It is still very close to the original policy, just slightly modified. Like a right turn still stays a right turn. It will not suddenly do a yaw movement instead of a roll pitch combination. So fortunately, we do not really struggle with the data here. For the hybrid aerodynamics modeling, though, which should be as general as possible, we indeed collected about 1 hour of flight time, which at 400 Hertz is a lot of samples.
Yeah, thanks. Do you think that the same process you took for dynamics simulation applies to perception simulation? So starting with low quality domain randomization, then learning the differences based on real data. Does that also work for perception, or is it fundamentally different?
So this depends a bit on the perception approach taken here. So if we argue we have an approach, let's say we have a vision-based encoder, and then you have a subsequent action network that you give the input to. In that case, domain randomization would need to make sure that your embedding space is completely explored. So you cannot just simulate, you cannot just augment rendered images by changing the contrast and the color. Because if you look at an image from, let's say, Minecraft as a game engine, this has nothing to do with the real world. No change in contrast and color will make Minecraft look similar to Unity engine or Unreal Engine, for that matter. So domain randomization helps if you're close enough to the goal, but it doesn't really help you too much if you're completely off. So if we look at a vision-based setting, it's probably more important to use large models that are pre-trained. Let's use some segment anything model, for example. Use large pre-trained models that have been pre-trained VisionNet or ImageNet or something like that. Because these models have already the generalizability trained in. They've already seen a lot of different things. So they would rather rely on this and then use these as an encoder, fine-tune on your specific environment. So have a high-quality simulation of your environment to fine-tune them on, and then based on this, train an action network. When you train the action network, you can simulate a bit of noise in the embedding space, you can perturb the images again, but you have a good prior. And I think that is really what matters more in a perception setting compared to a state-based setting.
Thanks a lot for the talk. How would your approach change if instead of one task, you need to do 1,000 tasks with a drone?
So let's assume for a moment the 1,000 tasks are at least a bit related in terms of it needs to fly. If a drone does not fly, it is probably not that useful. So all the tasks a drone can do are flying to specific points. And if we now would say we abstract parts of the challenge to a higher level planning network or so, you could even divide this into two parts. You have a part of the control architecture that needs to do low-level obstacle avoidance, and then you have a high-level planner. If you would use such an architecture, the benefit is that you can use any of the already pre-existing multitask settings that basically are multitask planning networks. On the other hand, you can also do something like conditioning. So we have a paper actually at this ICRA where we condition drone policies to fly at least at different speeds. This is not something completely different. This is still a very similar task, but it shows that there is potential in conditioning control policies also to achieve different tasks. Different tracks, for example. We could train a generic policy on multiple tracks. It would only get the next gate as an input of the next two gates. This will sacrifice some performance for sure, so we haven't done this in the drone racing task. But there are plenty of examples that you can actually encode more possible tasks into a policy if you are willing to sacrifice a bit of performance.
A quick question on implementation. What was the exact flight controller that you used for both the autonomous drone and the drone racing pilot?
It's Better Flight version 4.2. We do not use a PX4, and the simple reason for not using a PX4 is that the human pilots use Better Flight primarily. And in their experience, it has lower latency, it provides a bit higher performance on the top end of the spectrum, and it's also much smaller to install.
So you're driving the PX4 board using, say, TBS Crossfire Link, or what are you, and what was the higher level computer that was running on board the drone?
Okay. Drones have a Jetson on board if we use onboard control. We also have the ability to use offboard control. We talk about, we have a collaboration with Team Black Sheep, so we can use their custom protocol for that. We can also use a layered module for communication with the drone. So yes, we have a Better Flight running on an STM32F7 processor, is the low-level controller. High level is NVIDIA Jetson TX2 Quasar breakout board. They have a serial interface to each other. If we go off-board control, we use custom protocol with Black Sheep in collaboration to directly send the control commands. Latency is around 20 to 30 milliseconds max.
Any last question? Okay, then let's thank our two speakers one more time. So we will now start the last part of our workshop today. And that will be a breakout session and a discussion session. And Chiara is going to show the breakout topics again that you have maybe seen this morning already. And we have put up little markers on the walls. So 1, 2, 3, 4, 5 to 8. And I would like to ask all the participants to just pick one of their favorite topics, group at the different areas. We have 5 topics already given for you. So you can group there. And if you have some other topics that we didn't think about, you can go to station 6, 7, or 8. And then you have about, let's say, 15 to 20 minutes to kind of discuss internally the topic. And afterwards, we will have a little discussion in front again where we try to summarize what people have found.
So basically, they can only share. And I cannot tell you how long
Maybe before the audience, I would like to make a general question.
Sure.
I mean, we saw a very nice presentation about simulations of drones, but drones flies thanks to what? Aerodynamics. And like we saw in the last presentation, like no one of us actually simulates aerodynamics. So I wanted to just raise a bit this discussion. Like, is it needed, or would it be better if we will have a simulator here, like fast enough, able to incorporate aerodynamics? I mean, we saw that, yeah, we can refine models, but we also saw that it's done in open space environments. What would it be if, like, suddenly you are in a constrained environment and the environment changes? I mean, aerodynamics is also influenced by objects around, air temperature, and so on and so forth. Now I leave space.
I think one comment why we are here, or one reason why we are here at a robotics conference discussing quad rotors, and it has been so popular in robotics, is because the aerodynamics don't matter much. That because we are, I mean, maybe some of you are aerospace engineers and have studied aerodynamics, but many don't, and they can still get it to fly, right? So I think a major reason why this is so successful is that aerodynamics don't matter as much as, for example, in fixed wing flight. If you then really want to optimize performance in, let's say, very specific cases, very close to walls or something, it may be different, right? And then you may, learn that. But it's very, very difficult to model those. We only have qualitative understanding what's happening and no quantitative measures and lots of parameters to identify. So I think then a learning-based approach is the best. But I think a reason why this made it to robotics, right, and is not as much part of the, or not at all part of the aerospace community, is because of that it's actually doesn't matter much.
Yeah, that's exactly what I trigger. I mean, I also have my opinion that is somehow similar, but yeah, I wanted to see if someone else say, no, I really want a very precise aerodynamic model. Anybody? Huh? No, that's that's the point. Yeah, I think it would have been an interesting thing to see, is exactly like, if do we really need it all, or there are maybe the question is, are there cases, like very special cases, in which it will be very helpful? I mean, I honestly work on these tilted and tiltable propeller platforms, and there, I mean, the models became even more complex in terms of their aerodynamics, because every propeller somehow influenced the other. But it's true, as Angela was saying, I mean, we are flying, we are touching the environment, even without these informations.
I think one of the interesting cases that we might study is when we have multiple drones in a constrained environment and then one walks in the downwash of the other. These interactions still needs some study, because if you're in a constrained environment and you want to fly, let's say 25 crazy flies in some constrained area, how can you do that? And they will have at some point to fly on top of each other.
So maybe aerodynamic matters if you change everything, right? So that kind of you have different density of the weather, different kind of the gravity, so that if you have some understanding of the aerodynamic, then you may not be limited to specific case. That could be Mars flight. Actually, we saw from Davide's actually one of the slides that actually kind of talking about the future aspect of the flight. Of course, there are interesting cases. I think it could be definitely useful, but the also kind of your point that whether we need now or not, of course, I think it could be interesting. For example, I'm very interested in aerodynamic interaction. In my PhD, I looked at the ceiling effect type of problems, but it is good that you have also ground effect in your simulations. At least like if someone claims ground effect or efficiency in ceiling effect, so that we can have something at least like a benchmark or the same thing, same parameters that we can compare. But also, I agree with you in a way that, like you mentioned, you know, like a bit of maybe overkill cases. For example, with the drones, like I want kind of, you know, I mean, many questions also could arise, but, you know, the motor propeller sets could change the things, or the battery can change the things. The question is, like, do we need to simulate everything? And maybe that could be overkill at the same time. So maybe that's the case.
Yeah, I think one interesting case is we never fly these vehicles on top of each other, right? Because of aerodynamic effects. So you could say, okay, if we want to enable that, we need it. The only problem is we tried that and tried also to learn that, but overall there's just a lot of non-systematic parts or noise. So you will never get a really nice performance if two stand on top of each other, right? The lower one will, you can compensate for the, you know, the average force, but you will always have the wobbling. So yeah. So yeah, you can do something, but you will probably still won't necessarily want to do that, having two on top of each other. So.
Yeah, sorry for changing the plans, but yeah, it was a very interesting conversation. Thanks.
I actually really liked the change of plans. I think there was a lot of kind of dynamic, and since everybody is also tired and nicely sitting down, I suggest we kind of keep using the same format, and people can either propose topics, or we go by the topics right here and maybe discuss them. So let's start. Does anybody else have a topic on mind that we should start? Otherwise, we go through the list.
Sorry for that, maybe not very specific topic, but I have one, maybe kind of an style-based, maybe kind of an input for that. Would that be possible to define the workshops in very early phases? So maybe, of course, I appreciate that it could be hard to maybe define the time, because, you know, like, and maybe managing the things could be very hard in earlier phase, but maybe the subject would be defined very early. And if we know that, let's say, if we are working with a master student, so that we can define that master students in earlier phases and maybe get some understanding about the problem. Just this kind of an input for now, so that kind of maybe could be useful for future things. Thanks.
Thank you for the feedback.
I would like to ask the audience, what do you think is preventing us from having one single simulator that works all purposes? Like, what's the major issue there behind, like, not only about what we saw here, that, okay, we have computational limitations, we have yes, like different purposes, but in my opinion, it's actually that the community works so independently that there are very little joint forces to try to accomplish common goals. And where do you agree with this, and what can we do to improve and overcome that? No one.
Yeah. No, but it's a good question. Does anybody comment?
I mean, in a sense, it's good that we don't work on the same thing, right? Otherwise, will be a fight. And I also believe that especially the type of some of us research that we are doing, it's really platform dependent and could not work with another platform. And so it's sometimes difficult to meet all the requirements in a unique system. So I think it's a pro, like to also like let us explore a different solution and not like, you know, just converge to one solution and then maybe, but that might be just a local minima. And yeah.
But then how do you compare each other works? Like the only place I saw a benchmark was what Angela proposed, that then you would like to add this and have like a common way to compare each other work. But besides that, I see only individual efforts claiming that they are doing like the best, but not really a way to compare each other.
So maybe I can also comment on it a little bit. I think what we have seen today in terms of simulators is that some people just try to focus on making it work for a particular interface. Like in Angela's work, for example, one driving force was to make it work for OpenAI Gym. So you can kind of use it with maybe reinforcement learning. And in other works, we have seen that people just saw the need for a particular maybe sensing capability. So they use some simulator, maybe extended it to include another sensor. And then we have also seen very specific kind of applications. Like, for example, there were maybe 3 works or so here that looked at making it work for like multi-robot systems in a highly parallelized way. So how can we train much faster on, let's say, a GPU cluster? And so some of the things are not really divergent. So in principle, you could maybe converge to one simulator, but that's more in terms of features. Like, let's say you can create a modular simulator where you can enable or disable certain kinds of sensors, or enable or disable certain fidelity of your dynamic simulation. But some other things are maybe more like integrated, like kind of what assumptions you make in terms of interface, what you want to connect to is very difficult. Or do you have GPU acceleration support or not? It's also a much more fundamental design choice, I would say. Any other comments to, I guess that's basically question number 5. Should there be one simulator? Should there be many different ones? Or, I mean, today we have seen maybe almost 20 different simulators. Should we really have 20, or is maybe 5 enough? Okay. No comments. Then, I mean, yes, I would say 20 is too much, 1 is too little. And we definitely as a community want to converge to maybe a few. A few is good because it drives competition and it also allows us to have different ideas in the community. But at the same time, we really need this benchmarking, because otherwise, as a community working on UAVs, we will like fall behind in some sense to the other communities, because our work will just not be comparable, it will not be reproducible. And so one aim of this workshop is, and So we want to reduce maybe the number of simulators that we use in total, and that will allow us to really benchmark things much more. Okay, maybe question 2 is also interesting. So today, what is the question? How can we make them be interested to others such more people can reach them? So maybe, does anybody from the audience have a comment about that? My first comment is we should have a workshop talking about simulators. That was one of our motivations. But also, I think it's very difficult for beginners to just try to find what is the right simulator for my application. And the workshop helps. And there's also this one paper that we had, which is survey selection and integration of UAV simulators, which can be like a starting point for other people to try to figure out what simulator to use. And I think also from like our workshop webpage, what we try to do is gather a little bit the inputs that we have gotten from all of you guys and from the presenters, and try to at least have a link of simulators with some description, and that hopefully people can just be pointed to it so that they can identify what are good simulation tools. Okay, then maybe what about, were there any features missing? Like today, like almost all of the posters and also the talks always started pointing out something that was missing, and then they added it and they had like some cool application where it worked. But is there something from you in the community where you say, hey, I really want to simulate that, and there's no simulator out there and we really need it?
But this is maybe more related to the people doing physical interaction with the drones, that there is not something absolutely not done for that, at least for drones. So now I see, or like what I'm trying to do is to get have the drone community more closer to like humanoids, and this type of community where contacts needs to be simulated as soon as possible. While for our community, this has never been an issue at all. Actually, the less contact, the better, because that would mean crashing. But now that, I guess more and more of us are looking in this direction, maybe having, more like interest in simulating better contacts, be a very good add-on. I have some experience on that. Gazebo for the moment is definitely not the good solution. There are others, but then they may lack on the nice feature of Gazebo as a tool testing for your like software in the loop that's being presented.
Yes.
I guess on the other end of the spectrum, so I'm trying to train drones to avoid large weather phenomena. So training it to avoid flying in thunderstorms. So I'd be interested in finding a simulator that has volumetric cloud simulation. I suppose there might be some commercial simulators like Microsoft Flight Simulator that do that, but I'd be very curious to find out that's specifically designed for our area.
Maybe a follow-up question of the dynamics actually understood in that case. If you fly a drone into a thunderstorm, do you really know what will happen?
I guess that goes back to the earlier questions. Why don't we have the aerodynamic simulation or high fidelity? So I would be curious about that too. So in my use case, I'm trying to avoid flying into them and train that model to not fly into them. That's mainly using the vision.
Our competition that we need more visual systems and more. Sometimes you cannot really simulate all what you need to test over a visual application, but even though you would test, it's more work. Like
Yeah, there was this switch to a camera in the single very very limited. I know it's render more realistic scenarios. This is a limitation. At least if we want in perceptions part, that will be at least a step closer to this reality scenarios.
Okay, that's a new question. Maybe any other comments about like what's missing? Yes.
I want to go back to the question about simulating aerodynamics. And it's of course drones are like photos involved, and therefore people use them. And that's an interesting question. That way. But you can also look at the other way around, like why doesn't robotics also like why don't we see more like smart robotics on systems that are harder to fly, where you cannot explain the typical stuff? And so one comment has to be but drones have half an hour of time of flight time. Why do they have half an hour of flight time? Is because well the flight time is related to disclosing, and if you want more disclosing, then you are you're less robust to gas, and you're less to wind, and you have less inflow, and so you're more in the wind vortex state where like the air is coming back. And so if you just like in a way when you're on the corner of like kind of those very high disclosing, very maneuverable, but also not that efficient system. And so why don't we see like very smart, helicopter is like very efficient flying machine, so maybe having more quite intelligent.
So you're basically suggesting if we would have better models, we could use it to optimize our robotic platform. Yeah.
And there, of course, I'm like people understanding about aerodynamics and the dynamics and the interaction. I think it should belong to very important.
Very good point. Also, maybe to add to the dynamics, it's quite funny what we have in terms of simulation for like multi-rotors in particular, because you can very easily fly normal trajectories just doing path planning and then using a geometric controller. And then the other kind of simulators that we have seen here, they use dynamics, but all what it typically is Newton-Euler equations. So it's like very simple rigid body, and there's like maybe gravity. And then everything beyond that is basically not well understood, right? Like we have this like ground effect, the interaction forces between UAVs, and we have sometimes neural network models that can kind of in a data-driven way tell us what it is, but from a physics perspective, we don't really quite understand what works. And that's actually similar also to the contact dynamics. Like there's some people now in contact dynamics that can maybe simulate it somehow, but I think it's still not really well understood, and that's why it's so difficult to do good simulations.
What about like what the presented actually is, like a presentation, so their methodology kind of also including the data, then would it make sense to expect this also module, in the simulators, kind of we can also submit our data or somehow use our data and kind of also, like can make the simulator more realistic maybe for our particular case. Like, would that make sense? I'm not sure whether, of course, like all the simulators have different as well, the kind of motivations, but.
So from my perspective, that's super important, but it's also dangerous. And it's dangerous because we use a simulator to then create some behavior. Let's say we use reinforcement learning to find now the fastest quad rotor that flies. But if we use residual dynamics that are basically learned on data, we cannot be sure that the learned model doesn't do something very unexpected in an area where we haven't collected any data, right? And so we might just create very strange behavior by adding it. But I agree that like a simulator should have the ability to have these sort of residual dynamics. And as a community, we should also have better ways of sharing models or data to train new models. Yes. Okay, so any comment, or otherwise I will comment on it. And maybe to add, so I agree, that's like super important. And just to add, if you then want to use a simulator for, let's say, planning, it makes it much more difficult, because then you're basically in belief-based planning world and you have to do probabilistic rollouts.
I think we've tried for a long time to follow. It's hard, I guess. Do it. Like turbulence stall. But we can collect data, but maybe just.
And then maybe the data that would be more like a stochastic data set and can still help to have better controllers that maybe can do better disturbance rejection or even prediction, like in the weather models, that if we could say maybe we shouldn't fly in that area because there might be a disturbance coming up. Okay, now we had 2 questions there, right? So that goes almost to question number 4. So academia versus industry. And so I guess even broader, the question is, almost all the simulators we have seen today were kind of academic simulators that we use to like drive our research and look at a certain aspect. And maybe PX4 was one that is also relevant for industry. But I guess the question is, do we move in the right direction? Do we actually solve with our simulators problems that the industry also has? And is it even relevant for industry? Yes.
I think I have a small, doing a lot of work. You can sort of, I think these are quite similar, but slightly different. Here we are more interested in experimenting. Industry, sometimes they actually don't pay information to testing. Just want to do whatever demo or etc. But what I think the industry can provide is really full time where I think people that can maintain infrastructure, like do the heavy lifting, the boring work that PhD students can. But PhD students can provide sort of more insights on what should actually be done, because normally the industry people are not really interested in simulation itself, they just want to get something. So I think it would be very nice if there is some middle ground where the heavy lifting can be done from the industry, where they actually make the best a certain amount of time to make the infrastructure safe, and also the academia kind of benefits from the work, but also provide some value that the industry is willing to. So what are the financial things? So I think that's a general problem in all reports. But I think recently it's changing a bit, at least from my perspective, that companies understand that free riding doesn't always help. And it's actually not that expensive to maintain infrastructure. You actually sometimes need one guy that can do a lot of amazing work. So yeah, I think probably it would be very hard for one organization to do the heavy lifting, but if we structure it somehow, that they sort of take out the burden. It's a common problem in open source anyway, but I think like the more mature communication or servers, they figured out some way that share the burden. But I think simulation is something like an infrastructure very important for everyone.
I think also, and some companies are small, so yeah, they tend to share having lifting, but we see super fascinating machine learning. The big companies provide all this every open source platform, and from big companies like Google, Amazon, they provide infrastructure. So I think, and what do they benefit? I mean, the benefit is people do their state-of-the-art work in research on their platform, and they can directly transfer it to their business model. And the other is that they are trained, the people are trained in the systems that are used within the company so much faster than when adopt and integrate into the company. I think they have the benefit. And for recruitment, I think the big difference is that some companies are small. So there's not yet a difference. Otherwise, I think that there's a big difference.
I think maybe another like common option is, especially in the drone world, is to just sell hardware and then have the software open source, and then you drive your customers to your hardware because the software is better. So that worked in the GPU world quite well. And then another option that you see, for example, with the Linux Foundation, is that you focus more on selling kind of services to companies. So once you reach a critical mass, you will have some smaller companies that might need some features but don't have the ability to implement them, and then you can kind of donate some money to the foundation that will help you implement that feature.
They haven't taken. What's holding them back? What's the culture of the there isn't only one.
There's only one big player, right? And then a few. So there's DJI, and then what else? I mean, so DJI tried to more sell the full product, right? So for them, it's like the full experience from you buy the hardware, you get the software package that is closed, but that can achieve very high level tasks. But you can see even for DJI, they're slowly opening up because they're selling their research drones. You get a little bit more access to things. And I believe that if there's more competition coming up, that will also improve. Like there's basically DJI, and then there's PX4 based systems, and people who like PX4 based systems mostly do it because it's much more open. So you can put in all of your custom changes, including the low-level flight controller if you really need to.
There an equivalent difference of the data? So like we want to make a bunch of data-driven models, industry, and collect data on a scale that we cannot. That's research. Do you think there's a way to pass that data back to us with the model? There's not really a way to, but this feels like the scaling works for industry with collecting data, but they don't care about models. People like data, but maybe not.
I have similar question. I think the main issue for us is that so apparently the topic of fleet management, so they have kind of like it's actually operational flight dogs, they don't have weather control, for example, weather And then the vehicle configurations may vary about. Thought it was a good idea to just do some presence that quite long, but then realize that actually being a very good way to carefully. I think it would be really, really nice to say maybe standard vehicle that someone gets thing. A bit like the whole identification is the base stuff.
I think that drives home a good point about standard UAVs, right? Because right now we have this problem that there's only the bit-grade drone that is somewhat off the shelf that you can buy and fly fairly easily. But for many of us, it's maybe a bit too small to do, for example, vision-based research or to put our non-linear MPC directly on board. And other companies that were building bigger open source drones basically went bankrupt and don't exist anymore. And so now, from a data set perspective, we have the problem that, of course, some researchers publish their data sets, but it doesn't help you that much if you don't have also the platform. But I think in some other domains, like, for example, in autonomous driving, there were indeed some successful data sets, like the KIDDI data set, for example. And in the drone world, I would say it's still very much missing, and it would be very much appreciated by the researchers, both for perception, but also for these aerodynamic effects. Maybe another interesting point on industry versus academia is that we have seen a lot of the simulators are built in academia, and that typically means you have a master or a PhD student who gets very excited about a topic, and then they spend a lot of work, they build an amazing simulator, and then they graduate, and then basically you see the simulator on GitHub and no changes for 5 years. And one advantage in industry is that, of course, you have this like more continuous development, you also have documentation, and you can like offload more work to the next generation of researchers. So do you have any ideas or comments on how we can like get to more that level in the academic world?
It would be very interesting to get some inputs from also these companies. Maybe, companies particularly for the, like applications for safety critical systems. Let's say, like a SpaceX, because they need to bring this back to the world, right? When for the rocket sector, for example, or the vertical landing, they should have kind of interesting simulation environments for that actually to make this work. Maybe I would love to hear that, like what they do and what that actually, like simulation environment they use for that.
I think one of the problems is with the general because there is, how to say, anything students may work, meaning if they don't get to be that famous or if they don't get that use, like for instance, for kids or those, then you won't see that commitment from people, either the sections or those folks that like to contribute to that. Well, that's the major problem. Like for example, I expect that there will be like we need to create like bigger workloads that become more famous on materials instead of having thousands of them, thousands of small ones.
Yes.
So I come from from industry. Like, I come from industry. And we moved on to PX4 at one point. We had a very nice in-house simulation, and I moved to Gazebo, and it was a step back. I mean, like the aerodynamics was much. And I dream of like being able to have a phone and like just taking a picture of the phone and then having the aerodynamic model of the airplane that will be as good as what we had after, like, and I think that's possible. And in something like this, in the grid, then it will survive. The thing is, we kind of like we need to have something much better than the refractory or the simple to survive. But if you have something, we can just take a movie of like what the propeller looks like and what the airplane looks like, and then fit to like SDL to be specific, and then we can have a very nice model. I think that is something that is higher fidelity than what we have, and that's good.
Also, collaboration to maintain between researchers, maintain the simulators go on and keep going. If one generation of PhDs collaborating with another, like pass down to students, and then have like 3 or 4 simulators that are almost good, transport between them, but can still maintain them by increasing their collaborators using some platform like Bitcoin and so on.
And maybe also a comment from me about that. I think we often like think too much about, oh, we need to publish many papers, but it's not so much about quantity, it's about quality, and quality is also measured as impact. And an impact would be, for example, the number of stars you get on GitHub, right? So there is definitely a value for you to try to kind of maintain your software and get other people to use it. Angela has many stars on GitHub.
Years and look at the citation and how impactful it was when they published open source code. And so it's a big advantage. So your impact in terms of citation numbers is larger if you have code submitted, and GitHub stuff correlate the citation. So definitely we support exactly what you say, right? So open source code create impact in different ways, GitHub stuff and also citation. So for example, the top 90% of all papers at Europe over the last 8 years, the top citations have been published. So definitely, just support, basically data that supports what you said. Yeah.
Okay, maybe we should start wrapping up. Any other discussion topic you guys have? Yes.
That's where there are some issues that might be whatever it happens to be. But this idea of longevity, I think, is very important. It's nice to imagine that the community can push it up stuff, but we need ownership. Engineering money. And I think I saw that this workshop is responsive or at least supported by the TCD on areas. I feel like with an institution like that, especially they are point for maintaining something that lasts longer than a PhD, or at least something financially back in the help support. So what are your plans for all of that? What do you want to do at this workshop?
Excellent question. I mean, originally, we definitely wanted to write kind of a white paper about kind of also the results, what we have seen here, and maybe also doing like a sort of survey on the simulators. We have not really decided if we will have the time or capacity to do it yet. So it's always kind of a problem. Maybe what I have seen today here is that there's definitely no one simulator, but we have kind of seen that there's many simulators that kind of relate to each other. So you could run like a k-means clustering and the k you need is pretty low. And I hope that maybe also today with the interaction and the talks you have seen, you might have identified some other research groups that do similar things. And maybe you try to also converge a little bit. And I would say like our more immediate plans are to maybe also use the web page and maybe the TC to try to like identify these sort of groups so that people at least are more able to find what are good simulators, and then we can try to converge a little bit. Maybe you have more comments, Chiara.
There is an interest about workshop. Let's say it was not on the radar yet. Talk about simulators for your day. You had a meeting with the topics out there, very interesting. But for instance, this one is quite new to them. So I personally started to attract their attention to this, and it is not yet clear to me what they can do in practice for that. We keep discussing. My intention is discussing. It's a good point to make something complete with their support, or to maybe some financial support that they can provide, so we can do more complete action. Not clear yet what those actions could be, or maybe you have a context for this. I know we are wrapping up, so maybe we don't have time, but it's very interesting to understand.
And maybe also to provide some history, like the reason why we created the workshop is that I think almost all of the organizers were like about to kind of create their own simulator to solve some problem, right? And we noticed that we don't even really know what simulators are out there. And so we thought, okay, we should really try to do this survey, and it's less work to organize a workshop than to write a survey paper, turns out. Maybe it's actually not true, like it was more work than we expected. But I think like really for me, the main goal would be to provide some resources to especially people who are new in the field to help identifying what simulators are out there, and also what are simulators that are still actively maintained, right? Because today we have seen maybe about 20, they're still kind of active, but in total there's way more simulators, and some of them haven't been touched in like 5 years or more. Okay, then I think we're at the end of the workshop. We're at the end of ICRA as well. Thank you very much for sticking around so long. And if you have any more feedback, ideas, or comments, you can find our contact information on the workshop webpage.
Por eso te digo que so in order to get on the way using visual and I'm doing or at least I hope this is a project that's really exploration.